Was the extended lunch helpful? So the reason why I asked is that when we ran the course a couple years ago, somewhere between Tuesday and Wednesday, people were sort of mentally saturated. And it was also part of the time when people started checking their emails too often. You're like, your enthusiasm is still there, but you're away from work enough that you're wondering if there's something that you need to do. And there was one person whose PI had a grand deadline. And so that was a really hard course for her because she was sending like processing data and sending everything back. So we just didn't want to have you in too much of a crush in terms of your responsibilities. Because I know it's hard because you're away for a week, you're away from home, and we're just, as soon as you want to digest information, we're just going to funnel you more information, and now you're buried on your information. So hopefully it won't be that bad. But this is also the first day where we don't have a hands-on practical, where we're not going down in the lab, and you're basically stuck in this room for most of the day, and that can also be a little bit draining. On Friday, we'll have a poll. You can give us feedback on how well we did and the pace. Almost there. We have seconds to go. We like to be more or less within schedule.
And keep going. We should definitely stop for breaks periodically throughout this practical. And like, I don't know, maybe every 75 minutes or something, if we have a little pause, if someone could ping me with the like this is happening thing, that would be really helpful because I'm unlikely to remember myself. Should we designate someone to be that person? I'm looking at Abby. You look like you.
You're responsible.
You're responsible every 75 minutes from now until the end of time.
You can set your phone timer 75 minutes and go. Okay.
Abby also picked what I should eat for dinner last night, so there's a bit of a.
Okay. So where is Alister going for dinner tonight?
Oh no! It was.
Oh, Laura's picking the places. I just pointed at the menu.
Oh, okay.
I just held the menu out. It was a bit like everything looked good. What are we gonna do? Kind of situation. I was like, Abby, please.
Too much choice. That could be a dilemma.
It worked out well. It worked out well.
Okay, I think we're on time, so let's start the practical.
Cool. All right. How's everyone feeling? Carved up and slightly on the dip. Yeah. I will try to bring some amount of enthusiasm. I won't be offended if you are less enthusiastic yourselves or if you struggle a little bit, but let me know if you want me to slow down at any point. You get to choose how you want to play this in terms of how you think your current level is and how much you might benefit from the different ways that we run this workshop. So starting groundwork, let's get everyone on the same page. We are going to be using the command line interface today, not the nice web GUI experience that I showed you the preview of in the slides. So what this means is if you have not spent time on a command line before, you will probably find this a little bit more of a new situation than other people who have not. And what that means is, unfortunately, this is not a general intro to the command line tutorial. We're trying to get through kind of how to use warp specifically. So if you're in that case, I would suggest trying to buddy up with someone next to you, ideally who has a little bit at least of that experience. We're not doing anything crazy complicated. I'm not asking you to write scripts or anything like that, but it might avoid some of the basic foot guns that you can run into if you're really not used to working in a terminal and these kind of things. Okay, so you have the option, even if you are used to working at the command line, if you would prefer, you can also buddy up with a person next to you. It can mean that you're working through things together and you have a little bit of like interaction. If you prefer to work completely solo and do things yourself and you really want to know and make sure that you yourself know how to do this, then absolutely go ahead on your own laptop, work at whatever pace you feel is appropriate. I will be here and we will try as far as possible to follow along with me. Because I'm by myself, that also means that unfortunately coming and helping every individual with little errors and things might be a little bit tough. And so if there was someone in the room who is willing to be like a little port of call for these people with basic Linux, what does this issue mean? That would be super helpful for the kind of smooth running of the workshop. That way we don't have to interrupt every 5-10 minutes when one of these little things pops up to solve it. If anyone wants to be that person, please raise your hand. Hey, we have loads of people in the back. It looks like you can generally gravitate towards the back of the room, and support will be doted upon you. There will be lots of people. Really great. Okay, cool. So the way this is going to work is we all have laptops here, and we don't all have access to the same compute infrastructure. What I've done is I've pre-loaded a bunch of computers in a data center somewhere on the east coast of the US with Warp, an Empire dataset, and some remote desktop software. And so you guys have been told a couple of times to download this Amazon DCV client thing. Hopefully that has been downloaded and you've opened it and seen a white, simple looking box and not been 100% sure what to do with it. Yeah, brilliant. Into that box, you will type the IP address, the public IP address of this machine somewhere in a data center, and it will load up and we will be able to connect to it. So I'm going to do this now just to demonstrate, and then you're all going to get the information for accessing your own machine. And hopefully all of this works as expected, because I set all this infrastructure up myself, and it's always a little bit scary to be like, is it really going to work for everyone? So in my terminal over here, I can look at all of the instances that I have set up. So I'm going to connect to instance 0 because programmers start from 0, and then you guys get to start from 1 like normal people. That's great. So I'm 323973116. Is the text way too tiny up there, or can you kind of make out the things that you need to see? Slightly too tiny. It looks like this terminal doesn't have an easy configure this thing, so we might have to make do. You'll be coming up here anyway to grab these numbers that will say which one of these instances you will be working on. And so yeah, when you come up, maybe also note down the IP address of the instance that you'll be connecting to, and then we'll get to it. So once you put in the IP address, I didn't get this message this time because I've already connected to this particular one, but you'll get a pop-up that says, do you trust this host? If you trust that I am not trying to do anything malicious here, I promise I'm not, then please click this. If not, I'm sorry, you won't be able to participate. Once you get through that, you'll be asked for a username and password. And so the username will be workshop, and the password will be warpem 2024. And so I'm going to write that down over here so that we have a thing. Username is, don't like that color, let's make it blue. Username workshop, password warpem 2024. It's no longer 2024. I'm sorry about that. Okay, and then you should hit login, and if everything works, you will end up in a computer somewhere else. Magical. And what we're going to do is, it's the same password over here, so warpem 2024. We don't need to upgrade Ubuntu. Ubuntu is fine. And then, don't worry, you're not supposed to be following along yet. This is a demonstrate, and then once you've got into your instance, you'll go through this yourselves. You'll have about 10-15 minutes to kind of get going. You're going to hit the activities thing up here, and you'll see that we've pre-installed this thing called Visual Studio Code. This is a text editor. If you haven't used it before, it may not be your favorite text editor in the world. The reason we're using it for the workshop is because it has a nice integrated terminal with the text editor. And so we're going to be putting together a text file with all of the commands that we've run, and it can like allow us to kind of track the history. And then at the bottom, we will be running the commands that will be for this workshop. And so hopefully that will allow us to kind of move forward. So yeah, when you open it up, things should already be set up. So you've got this directory Scratch, which is in your home directory there. If you hover over it, you see it. There's a little text file with some basic instructions. So if you have any problems with this, with these instructions, make sure you tell me. You should be able to see the Scratch directory and the directory containing this Empire data over in this bar on the left. It says test out creating a new text file here. Let's call it processing. This is where we're going to do all of our processing. And then we want to open one of these integrated terminals. So hit terminal. new terminal, and then let's do that in the Scratch directory. And so here at the bottom, we have this terminal down here where we're going to run the commands, and then at the top we have text. I'm also going to try and modify my font size now. You guys don't have to watch this. If you're taking part in the workshop, anyone in the back, if you want to take part, you're also welcome. I think we've got enough instances for a couple of extra people, so that's fine. If you could come and grab one of these pieces of paper with a number on it, and also write down the IP address of the instance that you need to connect to, that would be great. Okay, so that should be now quite a lot bigger, which is great. I'm sorry I can't do this for the terminal over here. So you'll need to write down the IP address of the instance, or you can start trying to copy it directly into your BCD viewer thing. I'm sorry I can't make it bigger. Tell you what, maybe I can do.
Alister, are these extra ones?
Which ones? Extra ones?
Does it make a number?
Yes. I can make it bigger. Hey, problem solved, right? By the way, I really like this online drawing app thing. It's super simple. It's called TL Draw, Tiny Little Drawing App. It's really good for like things like this, or if you're like you want a scratch pad for drawing something, or it's one of these sort of solo passion projects of a random dude, and it's nice. If you could generally signal to me with some kind of positive body movement that you have managed to connect once things have worked, that would be great, so I get a sense of where the room is at. As users, you probably don't care about the details of this, and that's absolutely fine. But the infrastructure that we are using is me replicating what the IT team at Michigan did for one of their cryo-EM workshops a couple of years ago. And it's a really good experience. And if anyone is considering trying to run workshops in a similar way to this in the future, I think it's really good. The setup is a little bit of a pig, but once you've got it, it makes it really easy to run them again in the future. And I'm really happy to share the instructions for the setup that I went through and everything, if that's useful for anyone. We make this guy. Oh, he looks kind of evil. Let's. Not sure if it's better. What was that, sorry?
Happy eyebrows.
Happy, which direction are happy eyebrows?
Not slanty.
Not slanty, curvy. Hey.
There you go. That's much better.
I sometimes use an iPad connected to the Mac to like do the drawing stuff a little bit better. It works quite nicely as well. But... All right. Connected, majorly failing to connect, lost in the abyss, unable to follow the rest of the workshop because you have a white empty screen in front of you. No? Okay, cool. I don't hear unhappy people, so we'll carry on a little bit. The next thing to do, so the dirty little secret of almost all of these workshops that you'll ever go to is that most of the time, what you're doing is running through an already existing tutorial that exists somewhere. And so the real benefit is that you are in a room with us right now. And if problems come up, we can kind of help you through those things. Hopefully that helps you have the confidence to actually run through the tutorial. It's also a special space for giving yourself time where you don't feel pressured to do other things to actually run through this stuff. But if you have any lab mates back home or anything, do tell them, run through the tutorial. It's not that hard. You will get most of the benefits, probably. All that was also to say that if you have questions as we go along, something's not clear, please do raise your hand. If you have a question, you're probably not the only person who has the question. Yeah, we're here to learn. That's the whole point. Like, let's do the thing. So the actual tutorial is on the internet at this warpm.github.io/warp. Some of you might have noticed that the old Warp website, warpm.com, has disappeared from the internet. Dimitri forgot the password to the server or the account that manages that, and that's why we are at this less good URL. That is the whole story. And once we're at the website, we're going to go to user guides and then quick start tilt series. And so we should get to this page. And then if you get back to your home institution and you have an issue with anything that you come across either in the tutorial or when you're trying to process your own data, if you click over here, you'll get taken to the GitHub. You can write an issue. There are lots of issues. Promise not many of them are bad. Lots of them are people saying, it doesn't do this thing that we never designed it to do. And that's like, okay, it doesn't do that thing yet. But yeah, you can easily drop an issue. Making a GitHub account is super easy. And we do try to be pretty responsive. There's also a mailing list. You can contact us there. Please do. So we'll go back to the tutorial. As this says, we are going to process 5 tilt series of this Empire 10491, which is in vitro apoferritin grid that someone collected tilt series on. Obviously, this is much less complex than all of the data that you will ever deal with in your own projects. Please do not think that that is making this experience of running through this data less valuable. The whole point, and what I think is really useful, is that you get the experience of what processing really good data looks like. You get an experience of every step of the workflow, so that when it comes to doing your own projects, you only have to solve the problems that are specific to your projects. And so you know how things go in the ideal case. You say, okay, this isn't working for my data set, but you don't feel like, every step is a huge battle. You're like, I know that if I solve this one problem, hopefully the rest of the process should go kind of okay. The feeling of trying to sort of battle against probably multiple pieces of tomography software is really frustrating. And yeah, doing the tutorial does a lot to alleviate that constant tension and sense of frustration that builds up in all of us when we try and do this stuff. Okay, so yeah, at the end, we should get a roughly 3 angstrom map from just 5 tilt series. The fact that this is possible in just an afternoon is something that's only really come up in a couple of different places within the last year or so. You get to take your shiny apoferritin home to your university and tell everyone how excited you are that you know how to do tilt series processing now. It's going to be great. We're going to have a good time. The general overview of what we're going to do is we start out doing what is the common set of processing that you do if you're processing either frame series data or tilt series data, which is the initial motion correction and an initial CTF estimate on your frame series data. We then move on to tilt series processing. And so that's an extra CTF estimation step that takes into account the geometry of the different images and gives you more robust estimates for individual tilt images and the tomogram reconstruction. We also run template matching inside Warp for this tutorial because we have good in vitro data with apoferritins, and so template matching works. Template matching may not work for your particular solution. It's definitely an imperfect tool that definitely doesn't work in all cases. For other particle picking solutions, we can talk outside of this for how you might want to approach those things. If you have geometry, I really like to recommend that people try and leverage that geometry in their system. And then once we've picked up articles, we'll do a 3D refinement in RELION. So Dimitri, when he built Warp and M, he decided, okay, I don't want to rebuild the entire world because I'm already rebuilding enough of the world. And RELION was what he considered to be the kind of standard thing for doing these initial alignments in the field. And so he built around that. We use RELION for initial model generation, classification, and 3D refinements, both global and local in Warp. That's kind of the general architecture. Once that's done, we're going to run a multi-particle refinement, which is what Dimitri calls this like final optimization of everything, where you wiggle everything into place and have a more accurate description of what's going on and hopefully a higher resolution map. And so, yeah, without too much further talking, let's begin. So we don't need to download the data because it's already there for us in our AWS instances. So the very first step that we need to do for processing in Warp on Linux using Warp tools is create these things called settings files. Now, we have one of these for frame series processing and one of these for tilt series processing. We're going to create them both now at the beginning because it's easy and we have enough information to do this. And creating this file, it just stores a couple of parameters that we need to know about everywhere in the metadata for you so that you don't need to provide them to every single program as we go throughout the whole tutorial. Okay? And so what I'm going to do is I'm going to copy this. And I'm going to go back into here. And I'm going to paste. Now, if I were to just try and run this, I would end up with problems. Very important when you're doing command line processing, try to think about what the words on the screen mean and what the arguments are actually doing, because sometimes people don't account for things. And so, for instance, I found a bug when I was testing out this workshop. If you misspecify the game here, it doesn't actually check that that game file exists. And so later, when it tries to do some processing, it will fail. And it's a stupid thing that's easily avoided if you critically look at what is going on here. So where is our data? Here it says it should be in a folder called frames. In our case, it's over here. So I'm going to right click on that frames folder and I'm going to do copy path. And then over here, I'm going to paste. So the data folder is in this /data empire 10491 frames. Processing folder, I like to call the processing folder for frame series, Warp frame series, the processing folder for tilt series, Warp tilt series. And then we end up with frame series processing, tilt series processing, RELION processing, and then I put, if we try out different programs, if I want to do ISONET, whatever, I have an ISONET folder. However you want to organize things. I think this is a logical structure which tends to work. The extension, in this case, if we look in our frames folder over here, we'll see a whole bunch of files, and they are TIFF files, so the extension there is correct. The pixel spacing, it's 0.7894. If you didn't know this for your data, and you trust that the people who set up your microscope calibrated things correctly and serial M is set up well, you can run an iMod program called header on one of these files. So header, and then one of these files. Ooh. And it's so big, you can see that the pixel spacing there is 0.7894. So thank you to whoever collected this data, you've done a great job. The gain path, so this is one of the other things that we need to make sure that we specify correctly. I'm going to copy the path to the gain and paste it into here. You'll notice I'm right-clicking and copy and pasting. It's because on my machine, the copy and paste pass-through for the remote desktop doesn't work super well. It adds weird characters and stuff. If it works on your machine, great. Otherwise, either right-click, copy and paste. It seems to work better. In this case, the gain is flipped in Y relative to the images, and so we need to pass this -- gain flip Y. In general, if you want to know the set of options that are available to you when you run any of the programs inside Warp, there are two places that you can look. So one is in the documentation. We have this reference section, and there's a Warp Tools API reference over here. So we have general commands, frame series commands, build series commands. In the general section, we have this create settings. And so you can see all of the options that are available to you in a description of what they do. If you were doing ER processing, for instance, you would have to specify these parameters that are specific to how we group the frames within an ER file. If you're doing tomography, you need to specify the dimensions of the tomogram that you want to reconstruct. These parameters are there. And then, yeah, this is sometimes useful if you are trying to do something a bit different or seeing if there's anything different that's available to you. You can also, nope, that's not where I'm supposed to be. You can also run at the command line warp tools -- help. And the text is way too big here, which is potentially going to be a bit too big for some of the things that we want to do, but that's fine. You can see all of the different commands, the same as you could on the website there, and a description of what they do. And so, yeah, frame series, tilt series, all of the things. Anyone stuck? Questions or anything so far?
I want to see what's written for all the folders.
What's written for all of the folders? What do you mean,
Yeah,
sorry?
like-
In the top. Yes. So, is that okay?
Yeah.
Very good. So I'm going to start by creating this first settings file. I'm going to copy. And I'm going to run this. And it says settings saved, now trying to find the files. It found 328 files. Fantastic. And if we look over in our Scratch directory, which is where we're doing the processing, we now have this file called warp_frame_series.settings. This is an XML file. It's Warp's internal metadata structure. You don't really need to look at these things, but if you felt like you wanted to understand something or weren't quite clear on something, this is where you would look. And you can check all of the things in there. But don't worry too much about the details there. That's just an internal thing. Okay, so I should have prefaced this by saying that there's an initial bit of setup, and the first sort of half hour of the workshop feels a little bit slow. And then once you start processing, everything goes, and suddenly we're getting maps and results and tomograms, and it feels good. Okay, so please stick with me.
Good question.
Yes.
So this data set, if you go to Ampere, that's pixel size not exactly as this described here.
Okay.
So in this case, you don't care about this one, this initial pixel size. The author in the while Ampere 10491 actually put this on their website. The pixel size is 0.834. It's different to here. So we trust the Heidler image collection or just trust the author's update?
It sounds like there is a discrepancy. I don't know which is correct.
Okay.
This data was collected for Dimitri, and this is the number that we use to process it. So I don't know where that
Yeah, the
discrepancy
web
come from,
basically
which
the
is-
exactly web, so it shows the pixel size.
Yeah, I'm not sure. I think
I'm afraid of the author update their information. I don't know exactly, but in this case.
I don't know. For this tutorial, it won't make a big difference. It's a tiny.
But you also mentioned that one as the big size, although it's not exactly the same, I think, but it's still.
Yeah, another place where you can have a discrepancy is if the data are super resolution and they report the non-super resolution pixel size. That was what I thought was going to happen when you were.
Another about the ER, do things basically, you mentioned, that's parameters. What usually number? I mean.
So from frame series processing, what we typically try and get is one frame for every one electron per angstrom squared. And so one of the options when you do
Okay.
general create settings, ER group exposure. So fractionate the frame so that a group will have this exposure. I like to use
I cannot see it. Sorry, where are you going to see it?
So you are going to reference. And then the
API reference.
I want
It's a folder.
And that's my surprise.
But
The number.
yeah, aim to have 1 electron per angstrom squared.
Yeah.
I saw that. Okay, thank you so much. How do you define the,
All right, let's-
We'll talk about this later. We'll talk about this later. Okay.
wait, I think, because I have it in a. Right. Oh.
All right.
Could I ask if someone's using.
So
Is anyone using 12 or 21?
I don't think we're.
You're using 12? Is 12? Is this 12 or 20? So people got confused. Is this 6 or a 9?
that's a 12.
That's a 12?
That's a 6.
That's a 6. But this is 12.
Wait.
All right. So we're now going to do creation of a settings file for the tilt series processing. We're just doing this at the beginning because it gets us off on the right foot. And so I'm going to paste this one over here, and we're going to look carefully at all of the parameters again. So, oh, I'm going to make this a teeny bit bigger. Oh, the scrolling is so quick. Okay, so I want to create the settings file as warp tilt series.settings. That makes sense. I'm going to put all of the output processing in the warp tilt series directory. This also makes sense. The data folder, so the data that Warp uses to kind of keep track of some things about the tilt series processing is this thing called the TomoStar file, which just contains basic information about like which images are part of the same tilt series. Those will get created later. We are saying here that we want those to be in a folder called TomoStar. The extension, we put star.tomostar, that's what they'll come out as. Pixel size again, same thing. Gain path, we need to make sure we update that to the same as this. So let's do that now. Yeah, exposure, this is same as before, specified in electrons per square angstrom. That's fine. And then Tomo dimensions for this data set, these dimensions make sense. And having them specified here is like a weird artifact of having to maintain compatibility with the warp GUI. I'm sorry about that. It's just the way things have gone. So once we've got this, we're going to copy and paste this command down here to run things. So we're going to get this warning. It says the TomoStar directory wasn't found. That's fine. We haven't created it yet. We will do this later. It's fine. We have this warp tilt series settings file that's been created. Everything is A-OK. All right. So once we've got those two settings files created, we're ready to start doing some processing. Really good. I'm going to switch back to the thing here, and I'm going to again copy and paste this over here. So this command is called frame series fs motion and CTF. And so this in one call will do both motion estimation, so estimation of the motions between frames in your frame series data, and then also an initial estimate of the CTF. And so we provide it with the settings file. We say, okay, this is all the basic information about this data set that you need. And then we specify some parameters that are specific to the motion correction and the CTF estimation procedures. Now, you'll see this kind of grid parameterization in quite a few places in Warp. What you're specifying here with these three numbers is the spatial resolution of the parameters that it will fit for either, in this case, the shifts, and in this case, the defocus. And this is number of points in X by number of points in Y by number of points in Z. So when we say 1 by 1 by 3, what we're doing is we're saying I want to estimate a 1-by-1 grid of shifts, which just means one set of shifts for the whole frame with 3 points in time across the frame series. I didn't look at how many frames there are just now, and I can't remember it off the top of my head, but setting this for tomography data to 1-by-1 by n frames will give you just a rigid initial alignment of the frame series. It doesn't necessarily make sense to try and do more spatial resolution, like 5-by-5 or 10-by-10 or something in tomography data, because we have such low dose per tilt image. And so we try and keep this just as a simple, rigid alignment of the frames for this step. Okay. And then for the defocus, so the CTF grid, C grid, we say, okay, we want to estimate one defocus value in time for this tilt image, this frame series, but we want spatial resolution this time. We want a 2-by-2 grid. The reason we do that is because we can use this initial spatially resolved defocus estimate to say, does defocus change across the tilt axis in the way that I would expect for a positive tilt angle? So if we have a flat sample in the microscope, everything should be roughly at the same defocus, same distance from the focal plane. But if we tilt it, we know that this side should get closer to focus, closer to the focal plane. This side should get more defocused. And so if we say this image has a positive tilt and we know that the tilt axis is here, then we can look, okay, do the values get more positive on this side or do the values get more negative? And we can say whether or not what is happening in the microscope is what we expect for our model. So this is this defocus handedness concept that you might have come across, and getting it right is important if you want to do higher resolution tomography work. So we do an initial spatially resolved 2-by-2-by-1 CTF estimate so that we have access to this. How does the defocus change across the image from the very beginning when we do tilt series processing? Yeah.
Is that a constant? Are these constant numbers or we can change them?
You can change them to whatever you want. That's fine. For tomography, 1-by-1 by n frames tends to work for motion, and 2-by-2-by-1 tends to work well for CTF. I think there's also an auto setting for these parameters, but for the purpose of the tutorial, I leave them up and I explain them so that we get some intuition around what's going on. Cool. There are a couple of parameters here that, you should also know about. So how, up to what spatial frequency do we want to use for fitting the CTF? So depending on how good your data is, sometimes you might want to use more or less of the information. Typically, leaving this around 5 or 7 for tomography data seems to work nicely, and you don't have to worry about it too much. And then sometimes it can be useful to specify that you don't expect your defoci for the whole data set to be outside of a certain range. That keeps things just a little bit more constrained. You say, I expect the result to be somewhere in here, and then we will promise we will give you a result that's somewhere in here. Nothing crazy. This use sum thing is sometimes a little bit interesting. I won't go too much into it now, but for tomography data, generally estimating the CTF on the sum of the power spectra is the right way to go. The alternative would be estimating the CTF on the power spectrum of the sum. And yeah, if anyone's interested, we can talk about that a bit later, but we'll keep things moving. Out averages, so this is saying, okay, once you've done the motion estimation, then you also produce an average of those frames, taking into account that motion. And then there's out average halves. If you've come across this noise-to-noise based denoising, or these noise-to-noise based denoising methods, they require having 2 independent observations of the same signal with different noise. And a way that we can do that in cryo-EM is by splitting the frames into even and odd sets of frames, and then using those to then train the denoiser down the road. And if you want to do those kind of methods, you need to have that information, and so you can specify to output it here. Okay, that's all of the parameters explained. I'm going to copy and paste this down into here, and we're finally processing. We're getting going. Blast off. Is it going to work? The first thing it will do is it will try and find all of the things that it needs to process. That's fine. And then you'll see this connecting to workers. So yeah, we run multiple worker processes, as many as you specify, and it will launch those and then connect to them and try and communicate with them. And then it will start to do the processing. So this is going kind of slowly, and it's going to take about 20 minutes. That's not ideal for us being able to chomp through a reasonable amount of stuff in this workshop. So I'm going to go back down to the bottom here. And what I'm going to do is I'm going to add this argument dash dash per device, and I'm going to say 4. And so I'm going to, in here, I'm going to do Control C to kill that. And I'm just going to start again, paste, per device 4 halves. That looks weird. Let's just see what happens. Okay, so now we're connecting to 4 worker processes, and in this case, they're all running on the same GPU. What you will typically get is when you run warp tools, it will by default run 1 process per GPU that it finds on the system, and then you can say oversubscribe these GPUs because I have lots of memory. And so when these programs were originally written, the GPUs that most people had access to had about 16 gigabytes of memory. If you have now bigger GPUs and you're lucky enough to have access to, like, I don't know, you've got 40 or 80 gigabytes of memory, then you can, for most processes, get away with doing like what we're doing here, 4 at a time on each GPU. Any questions? Yes.
I can visit, how are you running these programs? Where are you running these?
I am running them. So I opened up a terminal by saying terminal, new terminal, and then it asked me which directory to open this terminal in, and I picked this Scratch directory over here. And so I am running these programs in the Scratch directory on data in this directory over here, and it will produce outputs inside the Scratch directory.
Okay, so now I run post frames, this series setting and then frame setting and then.
Yeah, frame series settings, tilt series settings, and then motion and CTF estimation. Okay, and so it's going to take about 3 more minutes, so we get to take a little relax. I will get to you in just 1 second. What we will see if we look in this warp frame series folder is that we have a folder inside there called average, which is starting to produce a whole bunch of files. We've got these motion JSON files that you don't have to worry about. We've got these MRC files, which are the motion corrected average images. We've got these even and odd directories, which contain the even and odd half sets of frames averaged according to the local motion in those frames. And yeah, that will fill up. There's also, this is useful to know, there's this per item log of what's happened when you've been processing each of these. And so if we were to open up one of these, we would see what happened on that process running the GPU work. So it received a command to load a stack. It did movement processing. It did export movie. It did load stack again. It processed the CTF. And yeah, that's the whole set of things that command ran. If you run into issues, the errors should be surfaced in a way that you see them from the command line. We've recently sort of made that a little bit better, but you can typically see more information about what has gone wrong or what's happened inside these worker logs. And if you post an issue on the GitHub, it's generally useful if you can provide them. Okay, Laura, there was a... I answered your question. So yeah, sit back, relax, have a sip of coffee, and then yeah, things will process for a little bit.
Did you kill your first job and that rerun?
Yeah, I
How did you kill that?
Control C
Okay,
once I've clicked in the terminal.
Sorry. I remember when you talking about the RELION to do the at the beginning, you said that RELION 4 is the one you can use precise the
We use RELION 5 actually, but yeah.
5, right?
Yeah. We only really use a few small parts of RELION. The reason that we use RELION 5 is because you have this refinement on particle stacks rather than 3D reconstructions of the subvolume. It minimizes the storage requirements for that step quite a lot. And yeah, potentially works a little bit better in some
Yes,
cases.
because I run this kind of data set before. So literally there's around 4 or 5 saying that's the if you follow the whole protocol, the instruction is around 4. So I was wondering if it had to be run
Which
around.
protocol are you talking about? I don't think it says
When you
RELION.
run the 3D refinement, get the whatever the extraction of the 2D of the after the 2C3, and then the complaint say that's format is RELION 4 format. It's later, but I think that's why I'm asking whether it's a RELION 4 or RELION 5.
So I see what you're saying. Yeah. Okay, the question was, I get an error message when I run my RELION, or a warning when I run my RELION refinements, which says there is some metadata in here that is in a RELION 4 format, upgrading it internally, whatever. And yeah, the reasons for why that is are boring and relatively uninteresting. Don't worry about it, it works. That's the solution. Okay. So it's just about finishing up. And so we can trust that we have images over here. If we really wanted to, I could say, let's look at one of these files. So I could copy the path and I could say 3D mod down here, which is the image viewer from iMod, and I could open up one of those images and have a look at it. Hey, we've got apoferritins. Change contrast, do all the nice 3D mod things that we're used to. But motion correction and CTF estimation, not a big deal anymore. And so you can kind of just trust that this stuff has run the way it's supposed to and sort things out later. Okay, so the next step is we've been treating things up until this point as if they are just frame series data. So the warp does not yet know about how these images relate in terms of what tilt angle they came from or how much dose they've accumulated. And if we want to do tilt series processing properly, we need to keep track of all of these things and keep an eye on it. And so we do this step that we call tilt series import. And I'm going to copy and paste this command over here. And then we're going to get going with this. So we use this MDoc format, which contains most of the metadata that you sort of need to know about which order all the images were acquired in. We grab that information from the timestamps in the MDoc files rather than relying on the order of the sections in the MDoc. The overall where the frame series processing was done. So in this case, we did that in a directory called warp frame series. So we specify that. The exposure per tilt. We need to keep track of how much exposure has accumulated throughout the tilt series. And so we tell warp about that here. The minimum intensity. So this, if we look at, say, the reference section, tilt series, TS import, and we look at min intensity. So this parameter allows us to do a basic removal of images if they have below some threshold of intensity that we might expect. And so the way to think about this is as you tilt your sample, it gets thicker. We know approximately that it gets thicker by a certain amount. And so we say if the intensity in that image falls below this number that you provide times that expected amount, then we will get rid of it. Something like 0.3 is very safe, and you could apply this to most data, and it will get rid of anything that's obviously really bad because it's just on a grid bar or something like that. Yeah.
What about max intensity? Sometimes that pixels that just blow out.
Yeah, we've had some people who've reported some issues in some cases when they have that. The recommendation is that you do your motion correction and then you run CCD eraser on those motion corrected images from iMod. It's a program specifically for getting rid of those really intense pixels. Yeah, and then other options there as normal. But quick note, if you just copy and paste this and then try and run it, you will get an error in your terminal. That's because there's a space after this. The reason there's a space is because I have this nice little note which says what this option is about, and then that forced me to put a space there. You need to remove that space before you can run the command. It's really annoying, I'm sorry. Bye-bye space. This don't invert thing, also super annoying. IMOD has a certain convention about what a positive tilt angle means in terms of how that ends up in the reconstruction. Supplying this flag, Warp has an inverted convention relative to IMOD for this specific thing. So by default, Warp will invert tilt angles. When we have processed this data before, to get the correct physical handedness in the tomograms, we need to flip something. One of the ways you can flip the physical handedness of the tomogram is by not inverting those tilt angles. It's more complicated. You don't really have to worry about it, but we wanted the correct physical handedness in our data for this tutorial. You can process everything up to super high resolution, even with the incorrect physical handedness, and then flip your map in Chimera or whatever at the very end. That's fine. But it's a bit annoying if you, typically it's a thing that you kind of figure out for your scope or wherever you collect your data, and then you just never worry about it again. But it creates this point of friction that I don't like at the beginning. And so the output will be these tomostar files that we talked about before, and they will end up in that tomostar directory. So let's paste here and run the thing. Ooh. Something. I made the mistake that I told you guys not to make, which was I didn't read and look critically at what the parameters were. So I said that we get the information from these things called mdoc, and I said they're in a directory called mdoc. We are running this command in the scratch directory. There's no directory called mdoc here, and so it didn't find that and it died. I did not specify the correct path to these mdoc files. They are in the data directory over here. And so when I specify that correctly, this is a great example of the type of problem that you probably will have the first time you use this. And you don't need to pull your hair out. You don't need to stress. Everything will be fine. Take it chill. Okay, found 5 mdoc files, passing them and checking this tilt intensity situation, figuring out which ones it needs to keep, which ones it's going to get rid of. And then it's going to create these tomostar files that we're then going to use to start doing all the tilt series processing. Almost done. Amazing. So, main metadata management hell escaped. We have managed to get out of this sort of initial slow part of the workshop. From now, everything should be much quicker. The output of that process was this tomostar directory, which has these 5, one for every tilt series, tomostar files. And they look like this. They are star files, which contain just basic information around, like, which movie is in this tilt series, what tilt angles do they have. It will, if the information is there, try and grab the tilt axis angle from the mdoc file. A lot of the time, especially if you use the Tomo 5 software, this angle is reported incorrectly. And so this is a step that can cause you issues later on if you don't supply this angle or have a look at what's going on. And so it's just a thing to be aware of. The dose is the accumulated dose. The intensities is what uses to check whether a thing should be included or not. And then mask fraction, this it's not really relevant for today, but Warp does have some tools for masking out beads and getting rid of them in images and things, and that's related to that. Okay, so we have our motion correction and CTF estimation done. We have tomostar files. We can start doing tilt series specific processing of our data. What's the first step in tilt series processing? In this case, the way we're going to do it is we're going to start by doing tilt series alignment. In this case, for this data set, patch tracking in iMod works well. We run this through a wrapper that we provide TS eTomo patches. If you want to run tilt series alignment your own way using whatever program you might want to run, we provide ways of importing iMod format metadata, and then We also provide wrapper programs for fiducial-based alignment in iMod and for RTOMO v1.3.4. Yeah, RTOMO hasn't changed significantly since that in terms of the core algorithm that does the projection matching. They've added more functionality for CTF estimation and things that we as Warp don't really mind about. And so you can use these wrappers if you want. You are in no way forced to. You can import results from anywhere if you want to do that. So let's launch this process.
So where do you define the initial axis? The value.
So the initial tilt axis angle, this is a thing that you should know for your scope. And if you need to estimate it, you risk being off by 180 degrees, because the way that you would estimate it would be, there's another program called, go over to this reference, TS stack. And so this will produce tilt series stacks that you can then look at. You would open up that stack in an image viewer and you would try and eyeball which direction the tilt axis is. The convention is angle counterclockwise from the y-axis. Open in 3D mod, different image viewers have different conventions. If you get that wrong by 180 degrees, rather than like this, then you will end up with inverted handedness in your final reconstruction, and it also affects the defocus handedness that we talked about before. None of these are irrecoverable issues, but it's a good thing to have a good handle on for your scope or your wherever you collect your data. Okay. So again, we had one of these phantom spaces here. So let's delete that before we run the command. We will copy, we will paste, and in the background, these worker processes will go and try. In this case, iMod already does a bunch of multi-threading and it's not GPU accelerated for the most part. And so it doesn't make sense to run multiple processes per device. So I've just left it at one process per device and it will do its stuff in the background. This will take 5 minutes or so. Patch tracking versus fiducial-based alignment versus RTOMO. Our experience, and I think the experience that a lot of people have, is if the data is good, RTOMO works really well. You can sort of just push the button and it will align things. But the results are often not, the only way I can describe it is as crispy as I would like. And so and maybe I'm just old school, still advocate for spending a little bit of time trying to fiddle with your tilt series alignments and things. And I think it really does matter how good these initial alignments are in terms of your ability to see your particles, especially if they're smaller, and interpret your tomograms. I see a lot of people trying to do averaging on things that are really poorly aligned. It's not their fault. They just don't know what good tomograms look like. That's another reason why doing a tutorial on some data that aligns really well is really important, because you see things. I spent about 2 years of my PhD processing data. The lab didn't have much experience doing tomography before this, and I hadn't processed good data. And so my boss just kept saying, oh, you need to make this better, keep trying different softwares, da, 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 da. And in the end, the data wasn't terrible, but it was never going to go to super high resolution. And as soon as I processed something that should work, I was like, oh, that became very clear to me. But unless you have that point of comparison, it's very hard to say, no, there's something wrong here. In that case, it was kind of interesting as well. The data, the grid itself was fine, but for some reason, when you exposed that particular grid, the sample moved a lot more. And so if you looked at the motion statistics, as you got to higher tilt, things were moving a lot. And there was like, 10 angstrom shifts in the motion correction in the first third of the frames for each tilt image once you got to higher ones. And the idea of doing any high resolution average when things are moving that much is unlikely to happen. That's why I said I like the way the Warp desktop used to put this information in front of you. It lets you see if things aren't as good as expected. So I mentioned these log files before. If we want to see what's going on, we'll say, okay, it's received Tomo patch tracks, it's running batch run Tomo. Thank you, iMod, for doing all of these nice things for us. It's running the alignment and it took 50 seconds. And so it's done that for these 4. And hopefully it will do it for number 5 soon. If you wanted to, you could see the results of each of those individual alignments inside this tilt stack directory inside here. You'll see all of the iMod files and things. If you don't care about that stuff and you're worried about disk space, you can set it up so it just automatically deletes those things. Sometimes it's nice to look at it, open it up in eTomo, you can modify things and then re-import the results. I think that's quite a nice workflow for more complicated data sets where you really want to spend time optimizing every series. All right. I think we're past the first 75-minute sort of block. I reckon let's take, no?
About 15 more minutes.
Okay.
If you want.
I started at 1:15. That's fine. I think this is a good point to take a couple of minutes, let people catch up if they are struggling behind a little bit. If anyone has any questions or any kind of things, I'm happy to take them now. But if you want to go to the bathroom or anything, please do. If you want to just like decompress a little bit and stop thinking about the terminal, that's also fine. Yeah.
When I read what those with the Atomo record and I looked at the log file, it said it was using Atomo 2, not Atomo 1. So I presumed it was using the version I loaded.
So
Atomo 2.
I tried to get it working with Atomo 2 at some point, and we import results from iMod metadata. So we ask Atomo 2 to provide us iMod metadata. Versions something to something, I don't exactly know where the bounds are, produced .tlt files with all zeros for some reason. And this was causing issues somewhere. So that's what led me to go back and recommend that people use Atomo 1. I might not have updated what it's using by default. And if that is, I'll check that and I'll make sure that's better for the future. But that's where that kind of, I wanted to stay in sync with Atomo, but they changed the API a lot and changed what it meant for a program to be called Atomo. It used to just be a tilt series alignment thing. Now it's trying to do everything. And that has made it particularly hard to sort of support multiple versions and stay in sync with everything.
It did work.
It did work.
Yeah.
Okay, well, I'm glad. Yeah, if it worked, that's good. But yeah, the recommendation is Atomo v 1.3.4, the last version that was released when he was at UCSF.
Could you go over again what the per device format? So
Yes.
That's 4 GPUs or 4 tasks?
That is 4 tasks on 1 GPU.
Okay.
Yeah. So the default is that you will have 1 worker on each GPU in your system. So if you have 1 GPU on your system, you'll get 1. If you have 2 GPUs, you'll get 2. If you have 3 GPUs, you'll get 3. And then per device says how many workers on each GPU. And so if you have per device 4 and 1 GPU, you'll get 4 on that one.
Yeah.
If you have per device 4 and you have 2 GPUs, you'll get 8 workers. 3, 4, 12.
Yes.
Yes.
So for 40 GPU or 40 gigabytes GPU with 4 GPUs, then what's the maximum value you can enter?
Honestly, the best way to figure out the max is to just try with higher and higher numbers until it starts crashing. When it starts crashing, that's too much. It's a little bit different per program. And so I have this recommendation based on like, if you have 80 gigabytes of memory, then try to use like 80 divided by 16. Amount of memory divided by 16 is a good first approximation for most programs. Yeah. Okay. Are things running? People aren't running into major issues. It hasn't crashed and burned for anyone. You had a question. It's crashed and burned for you? What's going on?
I think it crashed. I made the frame series, it made the print series. But after that, it crashed.
Okay.
I also have the file with last seed density processing.
Okay. How's it working for you?
No, actually, it's like,
you're working together on this computer over here? Okay. Is it working for you?
I think our small issue, it says it's say going by to all workers and done. But the last line of it says initial access command not found.
That's the phantom space thing.
Yeah,
Did you
so
guys see first?
when we copy and paste the commands, there is sometimes
the other one, okay.
yeah, there's sometimes an extra space that ends up here, and we need to just make sure that those spaces are not trimmed. I'm sorry about that, it's really annoying. Yeah, I don't have an easy solution for it, unfortunately, but.
What's the result would be, right? Seems like it's done, it did some work.
I would rerun it and make sure that you have run, because what it's effectively done there is it has not run the full command, it's run the full command up to something.
Yeah.
And then it should work in that particular case, but it's better to make sure that you're running the full thing. Okay. Yes.
So let me see the state.
Sorry, which direction? What do you want to see?
The thickness of that we say is around 11, line length. I think yeah, it's always ones.
Yeah. How do you get? And then you can copy and paste from up here down to here, and that's right. Yeah, you'll see the folders in there. But that's it. It's working. Okay, I'm going to move on to the next step now. And I think a good logical stopping point is going to be when we have completed all of the pre-processing and we have tomograms to look at. That'll be exciting. So if you've had a bit of a dip, we're going to try and come back up. We're going to be excited that we are getting towards tomograms. So, why can I not scroll down anymore? It's very irritating. So we've run our tilt series alignment. And the next step is going to be checking defocus handedness. So we have a little program that implements this defocus handedness check that I talked about before. So this is doing the thing where we check on either side of the tilt axis and all of the tilt images, how the defocus changes. I'm just going to run that quickly. It should run really quick. And if we've done everything the same way as each other, we should all see high positive correlation between what our model expects, how our model expects the defocus to change, and what it sees in the data. And so here it says, okay, average correlation 0.931. The average correlation is positive, which it says defocus handedness should be set to no flip. This is what it's currently set to. Everything is fine. If it said negative correlation, you would need to do what it says and set it to flip. And what that would look like would be this command here. TS defocus hand, set flip. Nothing too crazy there, so I'm going to keep on keeping on just so that we have some sense of momentum.
Can I volunteer one piece of information?
Yeah.
We investigated the space in the copy issue. We found a solution that might work in people. On your screen right now, there's a little purple icon. Click on that.
It doesn't copy the space. Oh, so good.
I have had one or two where there's extra, but the big ones are gone.
Alright,
Okay,
but that might be better than selecting the text and copying.
that's useful. Thank you. Appreciate that. Okay, so the defocus handedness check told us everything was okay, we're the best, and so we're going to carry on again. And now we're going to do this tilt series level CTF estimation. And so just to reiterate, what we're doing here is we've already done an initial get an idea of what the defocus is and how it's changing within one image. But now we want to get a more accurate estimate for every tilt image. And a way that we can do that is by knowing that these are all images of the same 3D object from different projection angles, and we know that projection geometry, we can kind of constrain the estimates so that they all respect that geometry and get better estimates for each individual tilt image. And this is one of the things that I think Warp does particularly well, and it's wrapped up in this nice little program, which we can just run like this. And takes a little bit of time, but we get more robust, nice defocus estimates. And if you were lucky enough to use the old Warp GUI, or if you in the future are lucky enough to use the nice web GUI, you will have visual feedback that tells you whether this estimation procedure has really added more useful information. In Warp on Linux land, unfortunately, just gotta trust us. But that's the setup that we have. I'm going to get things set up for this last step that we have to do before we have beautiful tomograms. We're going to do tomogram reconstruction next, so I'm going to copy this command over while that one runs. Warp tools, TS reconstruct, and all we need to know is the pixel size that we want to reconstruct at. Super simple. I'm going to get ready so that when the CTF is finished, and then we'll finally get to have tomograms that we can look at and kind of check whether we're happy that everything is going well, or if we need to go back and do some more with our tilt series alignments, and then we can take a little break. Yes.
In the tutorial, under the box, under tilt series CTF estimation, there's some tip about one, I guess, visual. Yeah.
Yeah.
Yes.
Ah.
So is this like a command that I run, or is this
Yeah.
that I add to the?
So I didn't talk about this, but I should have. There. Yeah. I got carried away because soon we will hopefully have this nice GUI. It's kind of sad moving from a world where you have beautiful visual feedback for everything that's going on to command line things where you have to like dig through files and figure out what's happening. To get around that a little bit, Dimitri and I added this program called Filter Quality, which all it does is it prints histograms for the different parameters that you might be interested in, either for the frame series or the tilt series. So it takes in your settings file, and then you just say histograms, give me histograms of these values, and prints them out to the terminal. And so you can see things like the statistics about the motion in the first third of the frames. So when we expose something to the beam, it moves more at the beginning and sort of stabilizes a little bit. So we show the mean of the motion in the first third of the frames. You can see the defocus. Here, we don't have a very big defocus distribution. It's mostly around 2.5. There's one image where clearly something's a bit different down here. It's useful information. Astigmatism, we have this nice 2D plot in the terminal. Wow, yeah, so cool. You can see kind of if you saw that all of your images had the same astigmatism, you're probably not running warp tools alongside your collection, so you probably can't fix it now, but you have problems with that data, or it might affect things. CTF resolution, so this is a goodness of fit of the experimental CTF that we observed versus what our model of the CTF says that the values should be at every spatial frequency. How well that matches up to what resolution is what's reported here. And so we can see a pretty nice uniform-ish distribution around 5 point something here. It's okay. Phase shift, if you were working with faceplate data and trying to fit a phase shift as part of your CTF fitting procedure, you could see those values here. I think for frame series fitting phase it works, but then for tilt series it doesn't actually. I'm sorry, I've been meaning to get to fixing this for a while, but you probably shouldn't be using a Volta faceplate to collect tomography data now anyway. This was a thing in like 2017-ish, and Rado, who did all the development of that, does not advocate for people using it. anymore. And so maybe soon with laser faceplates and things, this will come back, but we're not really trying to push people to using faceplate tomography more than they are. Okay, so we have finished our tilt series CTF estimation. I'm aware that I've zoomed through quite a few little processes now, so there's no files output really by the tilt series CTF estimation. It's just updating metadata inside these tilt series XML files that we have over here. You don't need to worry about that, but that's what's happening under the hood. And then we're saying, okay, please, Warp Tools, reconstruct our series into beautiful, nicely aligned tomograms. This should run pretty quickly. The directories over here, we'll see that a new one has been created called reconstruction. And in there, we have 2 files per tomogram. One is the MRC file containing the volume, and then the other is a PNG file containing just a central slice through that volume. This can be useful just for, if you're here and you're in a remote system and you just want to quickly see for that tilt series, does it look like things went completely AWOL or do they look kind of okay? But I always recommend, actually opening up volumes and taking a look at them. So, well, we'll look at all these slice images and things look pretty crispy to me. That's great. Yeah, all of them look well aligned. That's what happens when you work with really great data. And then if we wanted to look at an individual one, we can open it here. And so I like to zoom in a little bit. And yeah, I mean, you can really see details in each of these little apoferritins here. And as we slice up and down, I mean, you can even see like this is maybe a hollow ferritin, or it's at least got something inside it. Yeah, I am very happy with those tilt series alignments. This is great. Any questions or anything? We've managed to get to tomograms. We're happy.
Also, I think after you also can do the filter quality for the CTF fitting on the
tilt series.
Tilt series.
Yeah, exactly. So that's what that note is about. Sorry, Laura, I did kind of half respond to your question, but didn't actually answer the thing that you asked. Yeah, you can run that same program on the tilt series settings file, and you'll get metrics, and then you can also use this to filter the set of items that you're working on if you wanted to restrict to just a subset. It's definitely more clunky than a nice web interface, that's for sure.
So for this tilt series, you have 5 tilt series. What your standard? You probably want to filter anything. The tilt series you don't want, right? Or you don't care. In this case, the 5 are good. Seems all good.
Yeah, in this case, the 5 are all good. In practice, I tend to filter tilt series not based on just statistics of fits and things, although if they were really bad, maybe I would do it, but much more based on how well they align. There's no really good metric for how well a tilt series has aligned. There are proxies that give you some information, but there's no really.
So that's why you want to see the.
That's why you want to open it up and have a look. And
I see.
Also, we're doing imaging, right? Like we want to look at things.
But if you have, I don't know how many you're gonna have it, but if you have 1,000, that would be painful.
For sure. Yeah. And
okay.
so
I see.
This is one of the challenges for the field.
Okay. Thank you.
Can you exclude like individual tilts in Warp Tools manually?
Yes, but it's not as easy as it should be. Okay. I actually have like a little interactive program that makes it really easy for us to do internally, and I just haven't been able to release that, unfortunately. But yeah, for now, the advice is basically, I hope you're not really needing every single tilt series. Hopefully the intensity thing catches most of the bad individual tilts and you don't have to worry about it too much. If you need to fix it for something, there are ways you can fiddle about in the metadata to do it, but it's not an easy workflow with like a visual clickety-clackety, whatever. That will come when we have the nice web interface, etc.
So could you just like remove the tilt from the dot file and process it?
Yeah, that's one way you could do it. Or we have this Warp Tools change selection, I think it's called. program. And so you can say, okay, here's my settings file. And you can say, okay, here's the pieces of data that I want you to operate over. And in this case, you would say operate over this particular frame series file, and then change status to deselected. And so that's how you would go about doing it.
Okay.
Okay. Another question? Yeah.
So earlier when we imported the data, we split it into the half maps. When we do the reconstructed tomogram, are you using those to denoise it, or?
That is a good question. Yeah, let me take this through. How do I get to? Okay, so yeah, great point. When we did the frame series processing, we made averages of both the even and odd half sets of frames. That was so that we could do denoising if we wanted to. And then when we reconstructed tomograms, we did not reconstruct half tomograms with them. And so I will have to update the tutorial.
But like you can.
Yeah, you can. Yeah. So TS reconstruct over here has these two ways of doing things. So half map frames will also do reconstructions from those half average images. So if we added that and reran it, we would get those. I'll do that now just to demonstrate it. Sorry, I keep opening up the wrong thing. Can't see the little like grabby handle for. So yeah, if I wanted to do this, I would add a -- half map frames argument there. Let's copy that and then paste it over here. And now in our reconstruction directory, you'll see we have these even and odd subdirectories, and you would get even and odd half tomograms that you could then use to train a denoiser or do whatever you wanted.
Okay, but so the like the even and odd frame series are used to give you one denoise reconstruction. Like you would have to go and run another.
So Warp Tools has a denoising tool. It's called Moistomap. It's not within Warp Tools, but it is installed when you install Warp. So if I were to open up a new terminal, do that here, and then do noise to map -- help. Yeah, there is a program which trains one of these noise-to-noise networks between those two half things and produces denoise output. But it's not as nicely integrated. There's also some documentation specifically on this on the website. If we have time today, we can do that, and that would be good. But the focus is on getting from frame series all the way to the high resolution average first. Yeah, Dimitri also had his own ISONET implementation at some point, which has not seen the light of day. But a problem with ISONET is that it doesn't try, or I don't think it tries to be aware of the CTF and therefore how strong the information is in the tomogram at different spatial frequencies from each of the different tilts. If you take those things into account and do your denoising in a way that's a little bit more aware of how much you trust information at different spatial frequencies, you can get nicer results. This is a thing that may see the light of day at some point, but now I'm just selling you vaporware. Okay. So yeah, now you can see we have these even and odd half tomograms, and those are the required inputs for training one of these denoisers. Okay. Did we take a break or not really? I feel like a proper break would be a good idea. No? Brains frazzled? Brains okay? Frazzled. Great. Yeah. Okay. Everyone, please enjoy yourselves for 5 minutes, and then I'll chain you back to the desks. Yeah. Hey.
Well, thank you first because of how we can take up a bit early.
Oh, don't worry. Yeah.
But this is very nice. I will keep asking questions.
Yeah, of course. Yeah, no, it's great to ask questions. It's great to.
Because there's so many details on one flow. And then I want to say this is one thing I see out. They haven't reached the part called peaking because I think my peaking has some issue. I don't know which issue there is. So this is the start call there, and I found out it's not gonna work for us, but I'm gonna find after the question later.
Yeah, that's fine. That's fine.
Thank you.
Yeah.
Thank you so much.
Yeah, lovely to meet you, man. Lovely to meet you. Are you based at NYSBC or are you?
No, basically well, I working on the microbiology at microbiology, and then partially helping the POC, something like that. See, but I never touched it over.
Yeah.
So I learned a little bit and tried to process data, but I say
It's hard. It's hard.
I don't know
Yeah.
why it's exactly the same side. That's why I asked you a piece of question. And I say no. You know, at the stage you say that's the website that's a bond strong, only got A strong.
This is you. This is you. I see.
Yeah. I believe something about there.
Okay, interesting. Yeah. Oh well, I'm glad you're here. Hopefully we get to the good result today.
Yes,
Yeah.
exactly.
Okay, that's good. I'm glad I don't have to. If we solve it today, I'm glad we don't have to investigate.
I thought it was a peaking issue because the only difference is because I checked as a follow protocol and the meanwhile, for 6, I got 0 peaks.
Interesting.
So I can lower the threshold to 1 and I got 3,000 ish. I will find that later. Obviously today, so
Yeah, what I'll demonstrate, how to look at the results and see some things. It will be good. It will be good. Yeah.
So before we dive in. So we're gonna change. Software might not expect that. But also it's. Oh, it's a part. Yeah, that's right. That's right. So. There's some downtime. So is it?
Eventually I want evening.
So we're gonna run into a problem. Solve the
Yes, so should I open it or off?
Yeah.
Okay. How, should I uninstall it? Yeah. Is there a way to delete this?
Yeah.
Okay, just bounce.
See how that goes. Oh, it's called the laptop live. Oh, actually, start watching that. Yeah, she did. Call the folder where you ran. Replace the date. Download stuff.
Like in your.
Oh, yeah.
Yeah.
So that's fine. She said that these sandwiches. Yeah, proceed to make these sandwiches. Oh, I see. So just so the way you're upstairs. That's not a good way to do. Yeah, right. Yeah.
Yeah.
So you wait for a senior gun.
Yeah.
So in Amazon,
Mm.
You may have.
This is the thing with the recipe.
No, I don't want.
What do you mean check?
Yeah.
So is none of these activities, the COVID impact holidays next year,
Okay.
For awareness in later.
RM space dash R.
What's that?
When you get your $1,000. Okay, so then, out of there. I got three down for, oh. What is it?
So we say about the voucher, really wants to study that. So if you do our stash account.
You're going to like, it's the night either.
Sure.
So maybe it's just from where I tried to go the last time.
Oh, maybe, this will be better. That's.
Okay.
So I started at the top or.
Yeah.
Oh, what's it?
Already on. Oh, yeah. Well, you got one, you won't.
In the folder.
Yeah, you do something along the same lines. Just as you like.
Latest.
Okay, so this one is which?
I think this is, what was it, it's 0.
Okay, so yeah, that's the original.
What rules and that's not something, but it's separately on our server. Possible and what rules don't work together. Now they should. The collection can come down.
Yeah, I found out. So you can fry your things and.
What is what if you have the first time?
Which one is actually first on my actually?
This computer is hooked up for lunch each time.
Yeah. Okay. I see.
Yeah, the child.
So it's the original one, something I need to uninstall.
We are like that.
No, but in this,
Oh,
it's fine, it didn't actually. Okay. I'll do this as well. On right top. Oh, yeah. I can see that.
Everything's on.
So you don't have any of these? Like on this computer? We can still need to download all of the program. Okay. Okay, that makes sense. That's different than what beyond that one you have to so much want, right? Okay.
Downside of doing that is the file is actually. They're not so.
Yeah, well, I can see there also be a lot of issues with like conversion.
Yeah, so make sure. Yeah, don't worry. Yeah, it's a machine. It might be two separate conversations.
I bet. Even installing what's going on.
Right. But the hope is that you can run the scripts.
Yeah,
That you live with.
that would be awesome.
Yeah. I'm gonna that.
Yeah, I think especially if some of our computers are running than others. Like,
They can always do that.
some that we could get used for programs for. I don't know, but it is on. They do them all over.
Yeah, you have to compile it. Okay. So I think. So what happens?
Yeah, so right now I've just been like, I processed some things on my computer and then transferred my files.
So you know that helps a little bit too, it's cheap, I. First thing I recently found with that.
Oh, nice. Was your background in computer science or computer?
They can
Walk back into the room and you feel heat.
Okay.
Yeah, I've seen that.
Did I hear people say, I barely know what a CTF is?
No, tell me that. Yeah, sure.
Would people like to know a bit more about what a CTF is?
Yeah. You just watch the Grand Jetson video with like his head and like a whiteboard.
Yeah, we could. The simple explanation that I like is the drawing that he did. So let me just get rid of this thing. Where is this slide? Yeah, Grant Jetson's definitely like a sort of fatherly figure, I feel like, as well. He's got like a comforting voice and all of this stuff. Where's the slide? There. So you guys see my slide? Yeah. Okay, so in and please, the microscopy side of things is definitely not my forte, so this may not be the 100% smoothest explanation. If any electron optics people want to correct me on anything, please do. But my understanding is that as part of the imaging system, we have electrons which get scattered by the sample, and then an electron optical lens refocuses those scattered electrons. And so you have this unscattered beam, which some like 90-something% of the electrons that go through your sample are this unscattered beam. And then there's the nice weak phase scattering happens in like some small percentage of those. And then the image formation that we get is the result of the interference of those scattered and unscattered beams in this imaging plane further down the microscope. Okay, and then the reason that transmission electron microscopy is a phase contrast imaging is because the formation of the image that we get is the result of the interference of these scattered and unscattered beams. And so as we scatter to higher angles, the length of the path that these electrons take changes. And so you can just see this has a certain length, and then because this is a triangle, this one has gone out at a different angle, and so it takes a little bit longer to get down here, and it takes a little bit longer to get down here. And so you can, looking at the wavelengths of these electrons and these path lengths, you can see that as this wave re-interferes down here, it will either interfere constructively, or the peaks and troughs of the wave will align and you'll get constructive interference. Those are the peaks in your CTF. Have you guys seen a 1D CTF? Let's look at a 1D CTF. Oops. 1D CTF. Thank you. Prize buck. Oh yeah. I was gonna say no, but then I saw the Reese's.
Here, you can pass it along.
Okay, so I'll tell you what. CTF simulator. Let's really play with it. No, we want the 1D. This one. There's a next PYP one. Okay, I would do that, but I'm here. Okay, so in 1D here as a function of spatial frequency. So again, lowest resolution information down here, highest resolution information up here. The CTF is this oscillating function as we get to higher spatial frequency. And what that means in terms of this image over here is electrons that were scattered to higher angles. This thing, the peaks of this CTF, or down here, I'm not exactly sure what the convention is here, will be where we've had constructive interference at that spatial frequency. And then where you have 0, you've had complete destructive interference of those two beams. And then where you have the other one, you've had constructive the other way around. Yeah, this is the reason for the shape of this curve, is because those path lengths change and you get constructive, destructive, constructive, destructive, constructive, destructive. And then what you're seeing in 2D over here is like those one-dimensional curves. They can also change as a function of the angle, depending on how your imaging system is working. It might be either perfectly circular, or you might have different foci in different directions. And that's called astigmatism. CTF. You can approximately think of an electron microscope as a thing that takes a Fourier transform of the projection of the object, multiplies it by the CTF, and then back transforms it and gives you an image back and adds some noise to that image. Yes.
Building up on that, can you explain how faceplate works?
Can I explain how a faceplate works? In terms of the physics, like what actually is the physical interaction that's making the phase shift happen? No.
Why is it good? What's the point of it?
I just ate this with a paper on.
I'm assuming it has something to do with this.
It does. Sorry, that was disgusting. Okay, so here in the simulation app, what you will see is that, okay, let's first talk about, as a function of spatial frequency, what this curve looks like. So the very lowest resolution information has a contrast transfer. The intensity of that information is very low, right? And then as you move to higher spatial frequency, it gets high. You'll see that you start from 0 and end up high at some higher resolution than 0. So what a phase plate does is it tries to introduce a phase shift into that unscattered beam. So you're trying to make it so that the crests move a little bit.
The unscattered electron gets moved down.
Can't remember if it's the scattered or the unscattered. This is like where I get a little bit fuzzy on
But one of them.
things, but one of them.
I think you can do it for all of them because it applies that phase in the focal point.
Okay.
So the point at all, then what converge to.
Okay.
But then what is it called then?
The maximum phase that it can apply is 90. So then by like shifting the electron phase, it will increase the lower resolution they have. So supposedly building proof of concept.
So yeah, now that I think about it, it makes sense that it would be on the after they've interfered again when they focus back down. And shifting here means that it no longer starts at the lowest resolution from 0 and then builds up. It means that it starts at 1 and then goes down. So it means that your low frequency information is being transferred and you have higher amplitude of those signals at low spatial frequency. And so that's why you get this effect of the contrast being improved, because we see and interpret low frequency information more directly, and you get this nice strong thing. And then if you, so you can, we've all seen that you can do nice high resolution reconstructions from defocused data. So you can eventually get all of that low resolution information and accurately have it in your reconstruction. But if you're looking at individual objects, the overall area under the CTF curve, which is like the amount of information that is transferred overall through the imaging system, is a little bit higher if you can do this phase shift. And so that's where the motivation for a faceplate comes from in general. Does that kind of make sense?
Yes.
Cool. Okay. Let's go back into Warpland. So the password, if you've forgotten it, warpem 2024. And we'll go back into our processing. Okay, so we've reconstructed tomograms. Great job, everyone. Hopefully you have tomograms and they look pretty good. If you don't, please ask the people around you or gravitate to the back, and hopefully some people can help out. I'm gonna keep on keeping on. So the next step is we now are in this second block of the processing that I talked about. So I said pre-processing, everything up to having tomograms. We're now in this stage of, okay, we need to get an initial set of particle poses and potentially also an initial reference to align them to. And so in this case, we're working with apoferritin. And so lots of people have worked with apoferritin before. We kind of know what apoferritin looks like. And so we can use an existing template, in this case from the EMDB, of apoferritin. And we can do what we call template matching, which is searching throughout the 3D volume for all the instances of something that looks like apoferritin in all possible orientations. This is quite computationally expensive. I'm gonna run this, but because these tomograms are, they started at a very small pixel size, and then we've binned them down a lot to get to 10. So the start was at like 0.8-ish. So 10 angstroms per pixel is like 12 times binning. Can't remember exactly what the dimensions are, but this will run very quickly as a result. If you started out with a bigger pixel size, then your images would be bigger and this would take much longer. You might want to bin them a little bit more, i.e. specify a larger pixel size for your tomogram reconstruction to make it run a little bit faster. You need to kind of decide how much resolution you need for your matching. Yeah, so let's run this. While it starts to run, we'll run through a couple of the options. So you need to specify what is the pixel size of the reconstructions that you want to do the matching on. This subdivisions parameter is how we parameterize the set of angles that you search. So step 1, I guess, is a 30-degree step. Step 2 is a 15-degree step. Step 3 is every 7.5. Step 4 is every 3.75. As you go and do more and more subdivisions of the initial grid for the search will take a lot longer, but you will be searching more orientations, and so you should get a slightly sharper peak. What you need in terms of these parameters will depend on what you are matching and the resolution that you want to match to, and you might have to play with these a little bit to get a good correlation volume out. This is just, which EMDB do you want to use and what is the rough diameter of the particle that you're interested in matching. This just relates to some internal stuff about normalization. If you have symmetry, then you can restrict the search space to not search the redundant orientations that you would expect for your molecule. So only search, if you had C3, you'd only search 1/3 of the angles. That's useful. This whiten argument, what it does is it sets the, if you look at the amplitude spectrum of a tomogram, so how strong all of the information is at all of the different spatial frequencies, you will see that it has much stronger low spatial frequency components than higher. If you're matching and your information is good at higher resolution, so if you have good tilt series alignments, then equalizing the spectral power of all of that information up to 1, rather than having this fall off, you would bring all of that information up to 1, is a useful preprocessing step and leads to sharper peaks. And so if your tilt series alignments are bad, this will not help and might make the matching worse. If your tilt series alignments are good, then this probably will help. This option, check hand, if you are template matching against a structure, and we have helices and we have structures within this that are chiral, or they look different in the reflection, then you can check whether around the peaks that you get, if the lip structure matches better, as a way of checking the physical handedness of your tomograms. So if we had ribosomes, ribosomes don't look like the reflection of ribosomes, and so you can do the matching against the correct handedness of the ribosome, and you can do the matching against the incorrect handedness of the ribosome. And one of those should match quite a bit better than the other. And that's a good way of telling we have this physical handedness in our tomogram. All right. And so this check hand parameter is saying on 2 tilt series, check whether you get better peaks in one hand or the other, and then use that handedness for the rest of the matching.
Meaning there's 2 series or
2 tilt series, 2 tomograms.
so that's why in the file they have some flip. There's 2 files flipped.
Yes, exactly.
Are you applying symmetry here?
Are we applying symmetry? We are restricting the search space according to symmetry. We are not applying any symmetry.
So by 0 symmetry.
That's an O, not a 0. So it's octahedral symmetry.
Okay.
That's a good question. Good question.
So if I have a map that is, or I have a EM structure that's not released or not published, so how should I give the?
Yeah, so you don't have to use something from the EMDB. That's just an option that we provide. In general, field series, GS, template match, template path. You can provide a path to an MRC file, and you say template angpix. What's the pixel size of this? It will grab it from the header if you don't provide that. That's fine.
I don't need to do the Gaussian something.
Filtering or anything?
Yeah.
Generally, if you wanted to, you could. Generally, it's not required.
And if the symmetry is then if my symmetry is C2, then I just put C2 there.
Yeah, you put C2 there, exactly. Yeah. Okay, very good. So, template matching. What are the results? So, you'll see a couple of new directories over here. I'll just close down this one. We have template. So this is where the template and the flipped version of the template end up. If we wanted to, we could open those up and look at the beautiful apoferritin map. And then in this matching directory, we have way too many files. I'm sorry, it's a bit messy. For each volume, you will have a correlation volume. So this is a 3D cross-correlation image. And so what you would expect to see in that, if you had good matching, was peaks where you have particle positions. So high intensity where you have particle positions and 0 everywhere else. Angle ID is just a file that keeps track of the best angles for each of all of those positions in case you wanted to do something with that. This star file contains, in some RELION format, the positions of each particle. That's fine. You'll notice that these positions are all 0 to 1, so they are normalized positions from 0 to 1 along each dimension. You would, if you were processing this data yourself or wanting to interpret it, you need to multiply by the length of those dimensions to get the pixel positions. Yeah, and then in the pics folder, we have some diagnostic images which show us for thresholding at different values, how many particles you still have in each tilt series. And so it looks like the scores have changed since I wrote the tutorial, which means that if you threshold at 6, you will now not see any particles, apparently, or at least in the central slice, there are no particles above 6. But if you look at 3, we have quite a few particles there. It looks pretty good. And so I would probably to a first approximation, 73 for this data set. Yes.
Is 3, 4, 5, 6, is that like 30% confidence?
These
Or-
are standard deviations away from the mean across the correlation volume. And so they are normalized to the background intensity of the correlation volume for each tilt series, which means that they should be comparable values across different tilt series. The reason that that works is that you have many more background pixels than peaks. And so as you have more and more zeros and less peaks, and so you can just, treat that as your mean and background noise statistics. Okay. Cool. And then, same, you have this flip X and all of these things. I'm going to show you guys quickly. We actually wrote these pictures of just the slices. You know, what if you care about particles that are not in that central slice? All of these kind of things. We wrote a little visualization tool to allow you to kind of look at these correlation volumes and then simulate the effects of setting the threshold at different threshold values. And so I am going to demonstrate this. I don't recommend it. You guys can try and do this if you want. It should be possible to follow along, but don't worry if you don't manage to follow this part. So this tool is separate and needs to be installed separately. I've made the installation very simple, but if you're not used to installing things, it still might be a bit much for you. It says you have to install this thing called UV and then run UVX warp TM-viz. So I'm going to do this quickly. Installation is curl this shell script and then pipe it into shell. And so I'm going to go over here and I'm going to do exactly that. Paste that command into my terminal. Cool. And so it's saying you need to reactivate this terminal to make this program available. So I'm just going to move these zoom controls out of the way, make a new terminal. Why is the make a new terminal? Scratch up here. Okay, so if I do which UVX now, it's saying, okay, I found this because it's been installed. That's been fine. And then you can do UVX warp TM-viz. I'm going to run that. And it's going to install all the things that it needs in the background, hopefully nice and quickly and not be a huge pain. And this text is now insanely large, and so I can't really read. Okay, I wrote this program, so I should be able to interpret this. Hopefully you guys can too. I'm just going to write down the things that I need. So at the bottom here, I like to write out the commands rather than trying to get them at the thing so that you can edit if you make a mistake. It's easier than editing in a terminal at the bottom. So you've got UVX warp -GM-viz, and then put things on different lines because it's nice. RDIR, so the reconstruction directory is this. Paste. Matching directory -mdir is this matching directory. And then, MP, matching pattern. So in this case, I didn't look at the results for let's look. So in reconstruction, no, in matching, we only have two which have flip X, and that means that it found the normal handedness, the correct handedness to be the correct one for this data set because it went ahead and did the rest of the template matching with the non-flipped version of the template. And so we have these files, and then the pattern for the star files, which matches all of these, is going to be, and you have to put it in quotes to escape it, star underscore 15854 dot star. That is the blob pattern that will match all of the no, I need to put this matching / all of them. Okay, and then after the matching pattern, the correlation volume, we need to do the same thing. So it's going to be in this same directory. And then star_corr.mrc. And then last one is, do you want it to load volumes or do you not want it to load volumes? Let's look at the volumes because that's nice. So let's just try and run this. If you don't follow along with this, it's like irritating to type this stuff out, and I wouldn't worry about it too much, but I'll demonstrate this. The first time we non-relative patterns are unsupported. Okay. So seems like a weird constraint. I'm not sure why I wrote that, but that's fine. Yes. Okay. Oh, didn't find it. What's wrong with this? Scratch. So yeah, this is why I didn't really recommend that everyone try to do this, because it's easy to get wrong and a little bit irritating. But if you want to visualize your data, this is a thing you can do. You can also visualize it, whatever way you prefer to do. Field series reconstruction, matching directory. I am hamstrung by my ability to use copy and paste properly on this thing. Okay, ls, this. That seems to match. Why is it not finding the star files? Okay, 4. I'll try this one more time. If it doesn't work, I'm going to have to give up because we need to do things, and I'm sorry about that. Found 5 tomogram files, but not the... Okay, I don't know what's going on there. I'm sorry. We are going to have to move on. But what you get if you manage to get this running is a little way of switching through all the volumes at the bottom. So like a little drop down. You can change the cross-correlation threshold, and you can see the points appear and disappear on top of your volume that you would get for different thresholds. And so it's just a kind of useful interactive way of simulating the thresholding at different things. But moving on. We've run this, and so we need to threshold this set of particle picks. And so here the recommended threshold is at 6, but we will run it at 3 because it seems like the scores have changed at some point recently, and so 6 is no longer the correct value for this parameter. Okay. And so just in case you, you will kind of need to know what's going on here. So it's saying, okay, originally I found 3,000 particles in these star files. After thresholding, I have 1,500 left, so I've got rid of about half of them. Everything that did not have a score above 3 is gone. And so now we have these new star files here, _clean, which contain the filtered set of picks, or the thresholded set of picks. And so our next step is to...
if I change the threshold, the old file will be replaced, or
yes.
override.
Yeah. Okay, and so once we've done that, we can then output particles that we will use inside RELION to start running refinements. And so we can start going from, particles that we've picked and everything to actual 3D reconstructions, aligning and averaging all of these particles into one nice, hopefully high resolution map. And so I'm gonna grab this and we'll go through the parameters again as we've been doing for each command. Okay. Things worth understanding and knowing about here. So we provide the settings as we do with most of the files. This is nothing new or crazy anymore. We say, okay, which directory? There are two ways of providing inputs to this program. You can either provide one star file, which has all of your particles for all of your tomograms and says which tomogram they came from, or you can provide one star file per tomogram. Okay. In this case, we run template matching. It produces one star file per tomogram. And so we say, okay, here's the directory that contains those files, and here's the pattern that you can use to find the specific files that we care about. In this case, it's the _clean.star ones, the ones that have been thresholded like we did before. Okay. This normalized coordinates, it's specific to template matching output from Warp. If you do picking elsewhere, most of the time they provide pixel coordinates, and so you need to delete this. And then you say, okay, where do you want the output? In this case, I'm saying, okay, save the output star file that will be used as input to RELION in a folder called RELION and in a file called matching.star. Okay, I want you to output these particles at 4 angstroms per pixel. Why 4? Alpha ferritin is mostly made of alpha helices. And those alpha helices, or alpha helices in general, start to sort of separate from each other and resolve nicely at about 9 angstroms. If we have a pixel size of 4, that means we have a Nyquist of about 8. The fastest or the highest resolution information we can have in those images is about 8 angstroms. 9 is just a little bit lower than that, which means that we should be able to start resolving alpha helices in the map from these particles, ideally. What you choose here will depend on what you're trying to do with your data. Typical recommendations: start low resolution, move to higher. Alpha ferritin is a specific case where it's kind of featureless at low resolution. It's just a shell. And so you need to sort of be a little bit higher before it will start to lock on to where those helices are in the map. Okay. Diameter of the particle and the box size, you'll have to kind of, think about what makes sense. But general recommendation for box size is about twice the diameter of your particle. The diameter here is about, I think it's like 120. We say 130 to make sure we've got the particle within that mask. And then this relative output paths thing is a specific to rely on thing. Most of the time, you just need it. --2D at the end. We support output to either 3D volumes for each particle or 2D particle series. So these mini tilt series centered on the particle, which are pre-CTF multiplied. So depending on what you're doing, if for most 3D things, RELION works equivalently across these things. Some people report slight differences in how classification goes between the subvolumes and the 2D. Generally, we recommend 2D because it works a lot faster in the refinement, but if you end up running into issues, maybe try the 3D as well. Okay, so let's run this. And okay, I only gave this one worker, but it is a pretty quick process. And so what we will see is we have this new directory called particle series. It's like shorthand for particle tilt series, and a directory for each tilt series, which contains all of the particles for that tilt series. Now, a good thing to do at this stage, sometimes, especially when you're importing particle positions and orientations and things from other pieces of software, is especially if you've asked it to rescale coordinates and you're not 100% sure that you got all the scale factors right when rescaling coordinates and things, we output this file at the bottom. Oh, there's a lot of particles there, which is the average of all of the particles. And you'll get this when you do 2D or 3D export. Now, in this case, these are 2D images being averaged per tilt. And so let's just look at this image so we can get a sense of kind of what's going on. But what we would expect to see is apoferritin, the orientations won't be correct. It's just 2D averaging the image as it's been extracted. But it's a hollow spherical object, roughly. And what we see is roughly the projection of a sphere, centered in this case. So we can tell from this average image, I'll make it a little bit bigger. You can see that all of the particle images that have been averaged here probably contain an apoferritin, and it's roughly centered in the image, and that's a good sign. If you didn't have a hollow spherical thing, you would just expect more of a kind of white blob centered in the middle of your image. But yeah, this is a useful diagnostic output, and if you're taking particles in from somewhere else, it can be useful to look at these things.
Sorry, I missed this part. Where is the file?
It's inside. So you'll have in your tilt series processing directory, a directory called particle series. Inside there, you have one directory per tilt series. And then in there, you have all of your individual particle stacks and then the average of all of those in one tilt series.
Thanks.
No problem. Okay. So one of the other things that we will have got is this new RELION directory out here. So we asked for the output to be put in this RELION directory. We asked for a file called matching.star. We've also produced, because we did this 2D output, a couple of other files that RELION needs to do refinements. So this tomogram star, this optimization set.star, and this dummy tilt series. Don't worry about these things. Just they need to be there, otherwise things don't work. But yeah, we're now ready to try and do some refinements of these particles, which is great. So, yeah, in here, we've just said run this RELION command rather than doing it through the RELION GUI. I think what I'll do now is I'll demonstrate doing it through the RELION GUI because that's probably the most user-friendly way for you guys to get set up doing things. So what I'm going to do is, for this workshop, I've provided you with an initial reference inside the data directory that you can use so that we can start this averaging process and move a little bit more quickly through it. So this refinement and brute force searching over all of the angles is very expensive, and we're in a time-constrained environment here, and we don't need to necessarily wait like multiple hours for it to finish or whatever it might be. And so let's just have a quick look at this file. So if we do 3D mod on this file from our data directory that you guys should all have as well, over here, you'll see, oh, wow, it's a beautiful apoferritin. And what we'll do is we'll align all of our particles to this, starting from a little bit lower than what it is here, but not too much lower, and then hopefully see everything kind of converge nice and quickly. Sound good?
Can you use the whatever the template, basically doing the peaking?
Yeah, you should be able to.
Should be okay too.
Yeah. Okay. Very good. So what I'm going to do is change directory into my RELION directory. This is important. RELION wants you to run all RELION commands from within a RELION project directory. And we have made this RELION directory, which will be our RELION project directory. I have said the word directory too many times. So we go into here, and then we do RELION, and then we'll do --tomo to get the RELION tomography GUI. No. This isn't good. Okay, what we'll do is we will copy and paste. Yeah, I know I can fix this on my machine. I can't easily fix it on all of your machines at the same time. I'm not quite sure how this has happened because it was working the other day, but it's fine. Yeah, we will go back to here. Okay, so we'll say we change directory into the RELION directory. And then we will run this command, which is what the RELION GUI would have helped us construct for ourselves, rather than you're not expected to know what all of these things mean and exactly how to run RELION from the command line. They provide a GUI that makes composing this command easier, and you get to specify parameters in the separate tabs of that GUI. Copy, paste this here. Okay, so I hope that this doesn't cause us problems when we try to we will see. We will see. This could be problematic. Yeah, that's going to cause issue. Okay, we're going to have to give me a couple of minutes. I'm going to have to try and find out the set of things that I can do here that will then allow you guys to also solve the problem on your computers and then figure it all out. Take another break, enjoy it. I'm sorry. Okay. Magic
Okay, thanks so much.
Inserted myself in all of your systems and solved the thing that was missing. And if we open up a new shell inside VS Code now, everything should magically work. This was quite stressful. I really hope that we managed to still have enough time to get through a little bit of processing, but yeah, let's keep going and see how things go. Thank you for your patience. I really appreciate it. So, do we see the screen? We're good. Okay, let's go back in. War PM 2024. Great. So, to get a new shell, what we're going to do is we're just going to hit this little plus here and make a new shell in our Scratch directory again. That would be great. I'm going to keep our processing file open. Why did it get rid of the... Okay, perfect. So once you've done this, if you want to check that everything is now working, you can type LDD RELION. Oh no. Sorry, LDD. Wow, okay, don't worry about this step, but which RELION. This would check that all of the libraries that are supposed to be there would be there. If that doesn't show any errors, we're great. Don't worry about running this, it's fine. What we're going to do now is try and run this here. We will need to modify this command ever so slightly. So here we used a sphere as the initial reference and everything worked fine. What we're going to do is we're going to use this apoferritin. So I've copied the path of this apoferritin and I'm pasting that into the --ref argument over here. Ini high is the initial high pass, 40 is what they, sorry, initial high frequency cutoff. So we're starting at 40 angstroms. That's where we started for the tutorial where we're going to do a bit more processing. I reckon here, let's start more at like 20 so that we, you know, are giving it a little bit of stuff to work with. Hopefully it won't take too long to converge, but actually, for the sake of time, let's start it at 15. And then, yeah, we should be able to copy and paste this. Once we're in our RELION directory, not the Scratch directory, should be able to paste this and run. Okay, something has still not worked, maybe. Output directory does not exist. Okay, so we need to create, I thought that was going to be something worse than it was. When you run RELION from the GUI, I think the GUI creates this directory for you. And so when you run it from the command line, you need to create it yourself. Kind of silly. So the command to make a directory is makedir, mkdir. And so let's make this directory, refine3d. Oops. -P will also make the parent directories if they're missing. We now have this RELION refine 3D job 001 structure. This isn't great. Okay, I'm going to go back up to this big long RELION command and just try and run it. And it's starting to do our refinement. So as we set it up, it's starting our refinement this time from 15 angstroms. It will do the whole RELION thing. If you're not familiar with how RELION does refinements, basically it implements what it calls the gold standard refinement procedure, which you will start out with a reference at a certain resolution. It will split your data set in half, and then it will align up to whatever it thinks the current resolution is, all of the particles to that reference, and produce two independent, or to those two copies of that initial reference. It will produce two then somewhat independent up to whatever resolution your initial reference was, 3D reconstructions. It will then align those to each other up to 40 angstroms, and it will say, what's the FSC, the Fourier shell correlation, between those two half maps? Okay, Fourier shell correlation is as a function of resolution or spatial frequency, how well or how similar are these maps? And so there's a certain cutoff at 0.143 that we take as the resolution up to which we trust that these things are the same. RELION will then, in the next iteration, use that as the current resolution. And then the idea is that by gradually getting more and more, getting alignments that produce slightly better maps, you iterate and converge gradually towards the optimal map. Does anyone have any questions about that process? No? All seems kind of magic. I'll now speak less positively about it. It's not perfect. It is presented as this, if you just follow the gold standard, then everything will always be fine. It doesn't mean that you can't get overfitting. There's this tau fudge factor parameter that allows you to control how much the data is trusted versus how much prior is put on the model parameters. And if you play with this, you can see overfitting quite a lot. And also, sometimes there isn't enough information in an initial low resolution reconstruction to meaningfully improve the orientations of all of the individual particles. And so you won't gradually iteratively get better. You will just stay stuck, unable to really align any of the particles. And in that case, maybe introducing a little bit of prior knowledge or template bias would be a useful thing to help guide that refinement towards the correct solution. These things are not quite as black and white as they are always presented. It's important to keep these things in mind when you are using them, but it's generally really good. If you want another example of one of the fudge factors that's inside this magical machine, the way it chooses the resolution that it trusts is it actually looks at where the FSC crosses 0.5, so where the correlation between the two half maps gets worse than 0.5, and then adds a certain number of Fourier shells after that. And if your FSC drops off really quickly, that could be beyond your 0.143 threshold. You can also change that number. So you could say, add 50 Fourier shells, and then it would go way out. Obviously, the defaults are set up so that most of the time it's about in the right range, but it's not quite as free of arbitrary decision making as it is sometimes presented. If all of that went over your head, don't worry too much. You can ask me about it later if you decide you care but didn't understood. Yeah, it's a great program, but it is not the panacea. And sometimes I still use other refinement programs that give you, say, a little bit more control over the way the shifts and orientations evolve throughout a refinement procedure. So in RELION, you just say, for the most part, here you go, here's the initial positions and orientations, optimize everything. You can tell it to restrict the way that the angles evolve, and you do have a bit of control over that, and that's nice. You can't really tell it to control how the shifts evolve. Other packages, for example, Dynamo, that I use quite a lot during my PhD, you can say, actually, I'm really sure that I don't want my particles to move more than 4 pixels from this initial position. And sometimes that's really useful. Or I don't want particles to move more than 4 pixels in X, 4 pixels in Y, but I want them to move in Z. You can do things like that in Dynamo. They're not necessarily possible to do inside RELION. This is why I think it's important that we don't all just, blindly use these things, and also blindly think that our data are too hard or not going to work, just because RELION doesn't immediately spit out a high resolution reconstruction for you. Although hopefully on this data that we're working with today, it will immediately spit out a high resolution reconstruction, and we can all be happy with that. Okay, so good initial sign is that we're on iteration 2, and it's already sort of gone down to about the 11 angstrom mark. So it has got better than 15. It means it's like optimizing in the right direction, and hopefully after just a couple more iterations, we can stop it early and start using M to really wiggle everything into place and get a nice high resolution.
How do you kind of decide when to stop refining and RELION and go to M? Does it have to hit Nyquist or?
So RELION has internal stopping criteria. It decides based on a few things. I can't remember the specifics when it has converged. You can look at the maps, and if you yourself decide that actually a broad piece of advice that I would give is basically like if you're at 10 angstroms and it's at least done a few iterations, then that's more than enough to start optimizing in M. And if you're happy that your particle set are mostly the same 3D object, then I would say you can just go into M and it will probably be a bit quicker. If you want to do things like classify, it's useful to have really good orientations already before you classify. You can classify then without searching over orientation, it's much quicker. And so there you might want to wait until you get to a bit higher resolution and do a bit of classification and then go and refine in M. It kind of depends on what you're doing specifically, but I hope that gives you a sort of general sense. But yeah, the initial M results that were nice and impressive, I think it started at about 11 or 12 and then went all the way down to 3 in M. And so being at that kind of resolution wasn't significantly limiting in that case. I wouldn't stop it here, even though it's at 11, because it hasn't had a few iterations. And so there might be, even though on average the particles have got better, I wouldn't be sure that they are all pointing in the right direction after just this one iteration. Is anyone managing to run it? Is it working? The fix? No? Why not? As in,
I have a lot of errors, so I'm not really sure. I changed the reference file in the initial head 50 and I made folders, so not really.
interesting. I'll have a quick look because I'm still waiting for this to. But some people have got it running, so that like the fix that was deployed did get to these machines.
Yeah, no, this is just me.
Okay. Yeah. What is that? Do you understand? Have you come across a low pass filter as a concept? Okay, yeah. So we have the Fourier transforms, right? And the information is arranged as a. Okay, what is resolution in terms of images and in terms of like spatially arranged information? It's the minimum distance between objects that you can resolve them still as separate objects, right? And so if we have two dots do I see them as two separate dots, or do I see them as just one big blob like this? Make sense? Two dots, blob. A low pass filter is saying only let, it comes from signal processing originally done on like electronic signals and things like this in telecommunications. And so they had physical filters that they would put on things that were producing signals, put after things that were producing signals, that would only let the low frequency information through, or only let the high frequency information through. They have band pass filters as well that only let information above a certain frequency and below another frequency through. And so if you, when you're setting this parameter, what you're saying is only use information that is lower than 40 angstroms. So we typically in cryo-EM denote these resolutions in terms of the distance in angstroms between those 2 points that can be reliably separated in the reconstruction. And so 40 angstroms is a much bigger distance. And so if you can only separate things that are 40 angstroms away, your whole protein will look like a big blobby blob. And if you can separate things that are 15 angstroms away, that's much more information. You're getting a much better sense of where things are in space, but you're still not resolving things like alpha helices and other things. And so if we looked at those maps, we would see that the original reference had quite a lot of, you could see alpha helices and all this kind of stuff. After the initial reference used in the RELION refinement would be more blobby, but still have some. And then if we did a low pass filter all the way to 40, which was that parameter that we changed, it would be very blobby. Make sense? Blobbity blob. Okay. War PM 2024. It's taking its time, isn't it? Oh no, I just haven't scrolled down. It's been calculating, but it's still at 11 angstroms. Okay, let's wait for it to get a little bit further than 11 angstroms, and then hopefully run at least one M refinement, and that will probably be the end of the day. And if you wanted to carry on, the tutorial is online and you'd be able to keep running. When you run, I'll talk a little bit about how refinement in M works and how to think about it. So you need to provide good initial positions and orientations for your particles to M because it's a very local refinement. It searches very locally around the current positions and orientations of each particle and around the current defocus for each particle. M, you can choose between lots of different parameters which ones you want to optimize right now. And the correct choices for those things depends on your current resolution and how much confidence you have in things like your particle positions and orientations. We've thought about trying to make this a little bit easier to reason about and work with, but the reality is that it's a kind of complicated machine. And if you remove that complexity, you are actually making it harder to figure out what's going on and how to troubleshoot things if you have issues. And so we've decided that, at least for now, it's better that you try and understand a little bit what's going on and how it's working, and we don't try and hide too much from you. So I'll talk a little bit about the parameters that are available if we go back to the tutorial. There's a little bit of general setup. So you create this thing called a population. M uses terminology from there used to be this school of people who referred to the information you could get access to with tomography as like molecular sociology. It's like figuring out how all of these proteins look and how they all work together and do stuff. You have a population. There are multiple species within this population. A species is like a different 3D object. So you might have your ribosomes and your microtubules, or you might have your ATP synthases, whatever different proteins you've got. You can co-refine things potentially from multiple data sources. So a data source here is any set of data that has been processed through Warp together. So if you had like multiple data sets acquired on different lamellae over the course of 10 years, you could in theory co-refine everything together, and that's quite nice. This is just creating a mask in RELION. We don't need to worry about that. The species, then, we need to create this in M. What this is doing practically is grabbing the half maps from RELION, rather than doing, or in addition to doing Fourier shell correlation-based filtering on the half maps to provide an initial reference, M trains one of these noise-to-noise denoisers to denoise the half maps, because that gives you slightly better quality information in certain places. And if you have things like membrane leaflets, it smooths them out nicely because they don't correlate well between the two half maps. That's all fine. And then the first thing you do is you run M without actually running any computations to check that this has all kind of worked. What it will do is look at all the input data, not refine anything, so not change any parameters, and then produce an output map from the tilt series data. And you should see that this gives you a something about the same resolution or a little bit better maybe than your RELION reconstruction that you used as input with the positions and the orientations. Once you're happy that that's the case, you start getting access to parameters. So you have things like image warp. This is the 2D deformation of individual tilt images. Refine particles is saying refine the poses, the orientations and positions of all of your individual particles. CTF defocus is saying do a defocus search for each of these particles. So because we're at pretty high resolution already, we can optimize that defocus value for all of the particles and say, actually, we thought the defocus was 1.01 microns, but actually it's 1.004 microns or something. Then this CTF defocus exhaustive is, because the CTF oscillates so much, if you just try and locally optimize the CTF, sometimes that oscillatory nature means that it doesn't move in the way that it should to the correct solution. And so it does an exhaustive search over that. As we move down, we kind of rerun the refinement a couple of times. So as you do this, the positions and orientations get better, the image warping model gets better, your reference gets better, and then that allows you to better optimize those same parameters describing your system. And so things iteratively go up to the top. We add the ability to refine the stage tilt angles. So it's not 60-degree tilt, it's 60.1-degree tilt, something like that. We have the option of refining these higher order CTF parameters. So the model that we typically use initially for CTF does not match the data extremely well at high resolutions. And you can add extra parameters that will modify our description of that CTF that allow us to push to even higher resolutions, and gives you access to those things and allows you to refine them. You can then use this separate program called estimate weights to do data-driven weighting. So what you do is you say, okay, my current model of the whole system says that this particle should be here in this orientation. That lets you generate a very high resolution reference of what you think the data should look like here. And by looking at the correlations between that prediction of how things should look and your actual data and comparing those things, you can see which of your experimental data match your model well and which don't match it well. And you can say, okay, in my final reconstruction, I want to upweight the information that matches my model well, and I want to downweight the information that doesn't match my model very well. And this data-driven weighting is like one of the final little things you can do to push to even higher resolution if you want. And so I'll go through one more because it's there. We have this ability to say the particle is not at a fixed position. You know, we have acquired a series of images over time. It's possible that the particle has moved through space a little bit as we did the data collection. And so you can also resolve the particle pose over time, temporal pose resolution. This gives you access to that. All this is to say that M gives you the ability to refine and optimize based on high resolution references, lots of ways of describing your system. And these things, in the case of the absolute best data, potentially give you access to the highest possible resolution reconstructions. Most of this for tomography might make a tiny difference, but there's also a chance of overfitting these parameters. And so you have to be a bit careful, and you have to start out very conservative with these parameters and then iteratively add more and more things until you see it stopping improving. If it doesn't improve and the values of those parameters have changed quite a lot, it's probably overfitting and you should probably take a step back. It's a bit complicated if you're not used to thinking about models and all of this stuff, but it's, some people criticize them for this, and I think it's a fair criticism, but I don't think it makes overfitting is a term that people have a lot of kind of scaremongering about in cryo-EM. It's this evil thing that we need to avoid at all costs, and that is true. It is possible to do things wrong if you overfit to a template that you have grabbed from the internet. You know, you can pull out Einstein from noise, but just because this refinement engine is capable of refining all of these parameters does not mean that you should use it to refine those parameters in that way from the very beginning. Yes.
The differentiate map between 2.9 and 3.
By eye or by computer?
How can you say the computer is correct if you cannot see something like by eye?
The computer, what it's doing is it's saying, I have these two maps which have been independently refined by the system. So the refinement systems, M and RELION and all these things, they try to do a good job of keeping information separate. So you have two independent reconstructions.
I know, man.
And then you check how well these maps correlate to each other as a function of resolution. And then this one number that you see, it's just a cutoff on that line. And so the difference could be very subtle, but actually,
if you run one time, you got like 2.9. If you rerun it, you might get another number. The same map, you rerun it, you get another number.
If you rerun the estimation of the resolution, or if you rerun the refinement procedure?
You run the same procedure for refinement, you will get different results.
Because it's changing the parameters, which is leading to
You
different.
don't change any parameter.
If you run a refinement, you are changing parameters. If you run a refinement, you're updating the positions and the orientations and where this data comes from. So you are changing something.
Original data is not changing anything, right? We the same parameter, we just divide the same data into two, and then we do the cross correlation. We should get roughly the same thing, right?
If you don't change where you say the particle is in 3D space, which leads to you saying that it's here in this 2D image, here in this 2D image, if your description of those things gets better because you've been able to model that system better, then it makes sense that you would get a better reconstruction, a reconstruction which is more similar across these two independent half sets up to a higher resolution. I see where you're coming from, that it's a reproducible procedure. It's
But it's similar in single parcel, right?
It's the exact same.
Yeah.
Yeah, it's
I'm not just saying that it's a tomo everywhere.
it is a relatively good approach for validating our ability to say whether or not we have improved our description of systems. We use that description then to produce a reconstruction, and we can say that we are confident in those reconstructions up to roughly this resolution. So if we look at these curves, right, you have this Fourier shell correlation, and If this curve drops off really quickly, that's a really good sign. If it drops off really slowly, it tells you that probably different parts of your map correlate more or less well. And that means that, this one number is less meaningful in those cases. You don't have isotropic resolution. You don't have resolution that's the same in different parts of your map. This number doesn't capture that. And so I agree with your statement that the single resolution number is useless, but I don't agree with your statement that it is not a useful way of marching through frequencies and gradually improving things and getting a sense of how well your refinement is going.
My main concern is like 2.9 and 3. If you want to report 2.9 and you say it's improved, I don't agree with that. It's improved, but it just says a number.
Yeah, I agree that the difference between 2.9 and 3 is very small, and yeah. So a thing that people used to spend more time doing, and people in the EM lab still spend too much time doing, in my opinion, is modifying masks so that they include a really tight area around your protein, and trying to sort of game the FSC metric here. So if you change a little bit the set of voxels that are included in this calculation that says how similar these two volumes are, you can push this number just a little bit higher. And this is stupid. I agree with you that you need to be able to look at the map and say, is this really better? Is this not? But that doesn't mean that these metrics are completely stupid in all cases. Thank you. It was a nuanced discussion. Okay, let's see if we're going to get to run some M. Warp EM 2024. Okay, iteration 7, we're at 8 angstroms. I am happy with 8 angstroms. Are we happy with 8 angstroms? Yeah, let's be happy with 8 angstroms. Okay, Control C, kill the thing. And I'm going to go back now to my scratch directory, and then we're going to start doing M. So we're going to run this M tool setup. So first we do this population creation step. Ooh. Copy, paste. Okay, so running this has created a new directory called M, and inside it we will have a population called 10491. So this is Empire 10491. That's why it's called that way. We will then connect our warp processing to this population by telling it where our till series processing settings file is. And so I am going to copy and paste this. Fantastic. So it said it's found these 5 till series, and it's going to calculate some hashes of the data so that it knows that it has the correct versions of things. This is all great. Then we are going to, okay. We need to provide a mask for this refinement. So we ran this initial refinement in RELION without a mask because we didn't care so much. It was just a kind of initial thing getting us towards a nice map. But now we start to care about the resolution. And so we want to make sure that we're really refining the map and not just the random space around it. We will have to modify this path to the result. And so we have RELION, refine 3D. In this case, it's job 001. And I'm just going to run it on one of the half maps. This isn't going to be filtered. So I'm going to do RELION. There'll be a parameter here. It's probably -- low pass, but I want to check. Low pass, okay. So we are going to use iteration 6 half2.mrc. Okay. Moving things around. And then we're going to do -- low pass. Let's do a low pass to I don't know, 50 angstroms. So we just want to get a mask that generally encompasses our apoferritin. And then we'll output this to m/mask 4 angstroms per pixel. Okay, great. I'm going to do a quick have a look at this mask because I haven't checked. Yeah, great. So this generally is, M just needs a binary mask around your protein region. It will do the kind of softening around the edges and things itself internally. And so this looks great to me. It's not too featured. It's not really hugging the density too much. It's just, yeah, around our protein. That's great.
Where'd you get the input file again?
So it was inside our RELION refinement directory, and it was one of these half maps. So iteration 6 was the one I chose.
Any specific one? The last one?
The last iteration, yeah. Okay, and then now. So I'm now going to create a species, and I'm going to say, okay, in the initial set of processing, I want you to limit the resolution to 10 angstroms. It's a good starting point, and it lets us see that things optimize nicely. So I'm going to copy and paste this. The parameters that we have here, symmetry restricts the search space and allows us to symmetrize the map when it comes out. Doesn't really do too much. Temporal samples, this is that time resolved posting. One, if you don't want overfitting, especially as you get started, you can always change it later. The 2 half maps, the mask, the rely on particles. And so I'm going to have to change this to run job 001, and then it's not run data, it's run IT 006 underscore data dot star. And I'm going to say, okay, actually, I want to work at the what pixel size should I work at? It'll be a little bit faster if I work at a smaller one. Let's work at a pixel size of like 1.5. The max resolution we can possibly get is therefore 3. That should still be good. And then
We need to change job 002 with the other 2 lines.
This, yes. Yeah. The 2 half maps, you're right. Thank you. 6, half 1. Thank you, appreciate that. Okay, brilliant. So create species. So this is going to do this initial setup and train this denoiser. So it calculates some things about the map. It calculates FSCs and sees how much it trusts that the data are similar to make sure we're not doing anything too stupid. It then starts to train a denoiser. And so we want the map to be the best possible map that we use as our reference to align things against. And Dimitri and I think that these denoise maps, it's a useful thing to do. And so we'll have to wait a little bit for this denoiser to train, unfortunately. But hopefully.
Sorry, this the April picks 3 sample that mean.
So I set that to 1.5 because that would mean our Nyquist limit for the data which is 2 times the pixel size, would be 3 angstroms. While we wait for the denoiser to train, I can maybe explain why Nyquist is that. Sorry, did you guys want to see the thing? I heard noises.
Yeah.
Yeah.
I see is that just the half map MRC or is that?
This is the half map MRC, yeah. These are the 2 half map MRCs. This is the mask MRC. This is the run data.star for that iteration. All right.
I'm trying to bring up my paper. Oh my god. The right one.
Would you ever find if you said something?
So while we wait for that to train, I'm going to give you a quick back to theory land. Why is Nyquist 2 times the pixel spacing? It's a kind of thing that we are often told when we start doing cryo-EM, and then nobody ever tells us why, and we just kind of parrot it, and we're like, da da da. Actually, super simple. Let's say we have like 4 pixels. So this is our one-dimensional detector, and the pixels are separated by a distance, which we will call d, right? The fastest wave that we can represent on this detector will be one which shows us something like this. So it is oscillating very quickly between these high points and these low points. Because we don't have any more points on our detector, we can't possibly represent any wave which is moving more quickly, i.e. over a smaller space, than this one. The maximum, the wavelength that you see for this wave is 2D. And so this is where that factor of 2 for your pixel size comes from. The distance between the peaks of this wave is 2 times your pixel spacing for your sampling rate. Nyquist is no longer magical. It's a simple thing that comes out of a nice drawing. So if you just use RELION and refine it as far as possible, you will likely get stuck somewhere. The reason that you get stuck is because when you use RELION in the way that we're using it here, so you run refine 3D, all you are optimizing is for each particle, what position is that particle in the tomogram in 3D, and what orientation is it, right? And when you are using M, and RELION also has programs which do this, like Tomo frame alignment and Tomo CTF refinement, what you're allowing for is for the individual tilt images that make up that particle to shift and maybe rotate a little bit relative to each other. And so you've introduced this extra kind of degree of flexibility. You're not just saying, is the particle here, is the particle here? You're saying, how does the information within the particle move around a little bit to better match the reference?
This situation just for this team, ET
yeah, often you will get stuck at quite low resolutions initially when you do tilt series processing. And the reason is because your initial tilt series alignments are not that good, or sometimes they can be good for one part of your volume, but not necessarily good everywhere in your volume. And so this M and what NextPYP and all of these packages are trying to do is really give you the best possible description of that system so that you can then get the best possible reconstruction. Okay, because we've got another 5 minutes or so apparently, I will also explain how and why this noise-to-noise denoising thing even works. Like, what are we doing when we train one of these denoising neural networks. I'll leave that one up there because I like that diagram a lot. What are we doing? So let's imagine that we have an arbitrary two-dimensional space, and we have data points within that space, right? I'm going to say we have pairs of data points, actually, and maybe, what's the best way of doing this? These pairs of data points are two independently noisy observations of the same underlying signal. So in this case, there would be two particle images, and they have slightly different noise. Okay. What we are doing when we train a denoiser is we're basically making an assumption that there exists in this two-dimensional space, in this case, some sort of line or curve through this space. And that those two observations that you have are, because the noise is independent and Gaussian distributed, on average, those two noisy samples will be drawn from opposite sides of the Gaussian. It's just if you have a Gaussian and you take any two random points, on average, one will be over here and one will be over here. Okay? And then when you try and train this denoiser, what you're doing is you're saying, neural network, you are an extremely expressive, powerful function. You can learn anything. I want you to learn how to go from this noisy piece of data to this noisy piece of data. And so you start from here, and then you try and learn for every piece of data how to go to here. But the problem, or it's a very convenient, nice thing in this case, is that actually learning noise has no structure and nothing inherently obvious about it. And so you could learn to exactly reproduce for this input, give me this other noisy output. But on average, you get better at producing. There is less error when you produce the thing that is in the middle of this Gaussian, which is this clean, noiseless image. It's the underlying signal that is common between these things is easier to learn than the independent and high dimensional noise that you have. And so what we do is we try and learn how to go from this to this, and 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 this to this. On average, we learn how to map from noisy piece of data to clean piece of data, which lies in the middle between them. And what this looks like for two noisy half maps going to a less noisy average map in this case is a noiseless version of the thing. And it's really good at picking up these two maps are the same, these two pieces of noise are not the same between the map, and so I only learn to give you in the output what is actually consistent between these two half maps. And this is the same thing that's used in like Topaz denoise and CryoCare and all of these things. That was developed by a guy, Jaakko Lehtinen, who's like Finnish and works at NVIDIA now, and then is just picked up off the shelf and applied to cryo-EM. And it's a very nice thing because usually to learn things, useful things with neural networks, you have to have lots of examples of the solution. And this is actually a slightly different case where we don't have noiseless data. We've never seen noiseless cryo-EM data because if you have more dose, you burn the thing on the grid, and so you can't do that. But this sort of statistical phenomenon means that we can actually learn at least a much better approximation than what we have of the noiseless underlying signal that we have from these things. And so it's really cool.
Use this denoiser. We are starting from example.
With us saying what, sorry?
From water. I mean, you have like particles output from RELION, you have the refinements, you have like the mass.
So the different places in the cryo-EM pipeline where people have applied denoising are 2D image denoising. So if you want to denoise your micrographs, this is a thing you can do. If you want to denoise your tomograms, this is a thing that you can do. So you learn to denoise 3D volumes. And then here we are applying it at the stage of we have two half maps and we want to learn to denoise those. Warp lets you do all of these things. The utility of doing it for 2D micrographs is that it can make small particles more visible, but it doesn't necessarily the changes that it is making to very high resolution information, because that information is relatively or is very weak in the data, it's more likely to make mistakes with that high resolution data. And so we don't recommend that people denoise particles, for example, because it's not necessarily going to make the denoised image more true. But at low spatial frequency, it's very good. All right, let's go back to M. I'm aware that we've hit 5. Can we do one M refinement, stay until 5, 10 past, or do we up to the students? Okay. If anyone wants to escape, I will not hold it against you. I will not be offended. Please go and stretch your legs. I, just for my own satisfaction that we got somewhere today and didn't have a complete failure because of my lack of preparation, would like to finish. So whether or not you join me on this adventure, completely up to you.
You're scheduled till 5:30.
Really? Hell yeah. Warp. I was doing Warp EM 24, not 2024. Okay, cool. So let's have a look at our M directory. So we've created this species. Inside this species directory, we have a version of our alpha-ferritin. Inside this versions directory, you may see, in the end, multiple versions of this alpha-ferritin species. As we run M refinements, this versions folder will update with all of the different versions that you create. And if you need to roll back, this is how you do it. You go into that versions directory and you move the contents into your species directory. It's not a super nice mechanism, but it allows you to do these things if you need to do them. Let's say you see that you start overfitting, you can go back. There's no back button, but you can go back. And so we just spent a bit of time talking about denoising. And so what I'm going to do is have a quick look at that denoise map and make sure it doesn't look completely terrible. Oh, it's beautiful. We have alpha helices everywhere. We can see protein, but we can make it better. So that's what we're going to do now. So the recommendation is to first, where are we? Over here. First run one of these M refinements without doing any optimization of the parameters. And so it's just going to run and then do a reconstruction from where it thinks everything is right now. And so let's do this. World's worst refinement. It doesn't refine anything. We could have a separate program that does the reconstruction and things, but we haven't got around to writing it. And so this is the solution that is in place. Jeff before was saying something like, oh yeah, the worst thing you can do is have a solution that kind of works because it means you'll never get around to doing the proper thing. So yeah, unfortunately the reality, but luckily that means this refinement should go really quickly and will tell us. And so what I expect to see here is that despite the fact that we've started from a RELION refinement that only went to 8 angstroms and low pass filtered things to 10 angstroms, we should actually see a little bit better of a map coming out of this than those numbers. Maybe that's not going to be true in this case because we didn't let it refine for as long. But yeah, you sometimes see this, like even if you have a RELION refinement and you only let it possibly get to 9 angstroms or 8 angstroms because of the pixel size you set. It might end up going a little bit further than that once you, let all the information back in. And so this gathering intermediate results, reconstructing and filtering, what it's doing is it's saying, okay, where are all of my particles in the tilt images? And then it's going and it's grabbing the particle images from the tilt images, and then it's using them to do a reconstruction. The reconstruction process is that placing of these images as Fourier slices in a 3D volume at the angles that everything says it should be.
Approaching him, how do you decide what kind of refinements to run? Do you like try them all and see what it looks like?
So something I should say is this tutorial, because it's supposed to kind of get you through, it's not very conservative. This initial set of parameters where we use 6.4 image warp straight away, and we refine the particles and we immediately refine the defocus and all of these things. This is quite aggressive, and we can do this because we have an already quite high resolution alpha-ferritin map. So when I personally do things, I start with only refined particles and refine image warp one by one. And so what this is effectively doing is it's only optimizing global shifts. The whole tilt image needs to move a bit over this way or a bit over this way to shift everything into position. And as it does that, it also allows the particles to move a little bit to account for any little errors that, if I used to think the image was over here and that best matched these two particles when they were here and here, maybe as I move it over, actually I need to move the particles a little bit to keep everything optimal. And then I will rerun one by one image warp multiple times to really get the best reconstruction that I can get without introducing more parameters that can then be overfit a little bit. If I'm beyond 7 angstroms, I will start to add in defocus. And then if I see that I stop being able to improve with just one by one shifts, that's when I start to add in maybe 2 by 2, 3 by 3, or in this case, it's 6 by 4 because it's K3 data. And so you have that slightly rectangle detector. And then, it's the thing I was saying before, where being very conscious of what you're doing when it comes to choosing the parameters, it's hard when you first come to it and you don't really understand the details of all these things. But hopefully you have a little bit of a better sense of things now. Start conservative, play. I've definitely seen when people were using desktop M, I would go and see what people had got to after a while. And I would look and they'd started their species with 4 temporal poses, and they immediately were at 5 by 5 image warp and all these things. And sometimes they got slightly better results, but sometimes it didn't improve or it got worse. And restricting these parameters made things a lot better and made things kind of work. And so it is a thing that matters a lot, and it's hard to communicate how to use it effectively without having a forum like this where I can kind of calmly explain, maybe not that calmly, I've had a lot of coffee, calmly explain how to think about these things and what to sort of take into account. Ask on the mailing list as well. You say okay, I'm at this resolution, this is what my map looks like, this is, what I'm doing, what do you recommend? And I'll jump in and I'll be like, oh, hey, nice to hear from you. It looks like you should be okay doing about this. This thing about 7 angstroms for CTF, your CTF estimates are usually pretty good. They come out of the warp tilt series CTF estimation, and so changing them doesn't significantly change the way the curve behaves up until about 3, 4, 5 angstrom kind of range. And so it's not really going to make a big difference until you start getting more towards those resolutions. Although if your numbers really are off, maybe it can, but your ability to accurately fit those changes drops off quite a lot as well. Okay, scared to open it back up. 6.3. So things are kind of starting to go a little bit, which is great. Let's now run an actual refinement where we actually refine some things. So remember, we just did a reconstruction there. Now we're going to actually refine some things. Bam. Bam. Okay, and yeah, as I said, this is decidedly not conservative, but in this case, we have very, very good data, and so we can be a little bit not conservative for the sake of moving more quickly through the tutorial. Again, we've got this per device parameter. In this case, we have to specify that it's for the refinement step because there are other steps that you might also want to parallelize things over, and they have slightly different memory requirements. Yeah. Fingers crossed that yeah, this works out nicely and that we end up with a nice crispy map.
The per device works for CPU bound jobs and GPU bound, and automatically like
It will distribute the jobs over multiple processes.
okay.
But yeah, whether or not it's a smart thing to do depends on how that CPU job is implemented. And so the only CPU jobs that we have really are the iMod things. Everything else is GPU defined inside Warp. And yeah, as a result, per device is mostly splitting stuff across the GPU. It's kind of annoying. Hey.
And you are trying to using this solving metric instructions.
Yeah. I would even, this is being recorded?
Yeah.
For wide public distribution or for?
We can redact.
A thing that I have heard quite a few people complain about is RELION not behaving well for membrane proteins specifically. If you've got membranes and things, it just seems to not love that. It's a thing that M has worked well on in some cases for some people. A thing that's really important when you're working on membrane-bound targets is to try and remove the membrane from your reference because it's this very dominant feature in the 3D volume. And so quite often what happens is all of your particles will align so that the membrane is perfectly overlaid, but your particle that you actually care about is like a little bit more above. And yeah, if you, the easiest way to do it would probably be to use something like volume eraser and then make sure you low pass the map a bit so you get rid of that sharp edge that you've introduced. And that's okay. It's not the most principled, it's not the most elegant way of doing it. There's also this piece of software that I mentioned earlier called Occupy, which Occupy RELION. So one of the things that you can do with this is Occupy allows you to modify the intensity of different regions of your map differently, depending on what it thinks the occupancy is in that region. And one interpretation of the occupancy metric is somewhere where things don't match as well between maps. And so flexibility can also contribute to this. And membranes are typically, they come up at lower occupancy in this, when you compute this metric for every point in your map. And so what you can do is you can downweight the things that are at lower occupancy and upweight the things that are at higher occupancy. And you end up with a map like over here, where you see that the messy overfit membrane density is like completely gone. And the rest of your map looks really great. So this is it at one threshold, and then this is it at the other threshold. You can see that at low threshold and at high threshold, the membrane is completely gone. And that might be a much better reference to use when you start this refinement process than the one that includes this big chunky membrane. Yeah, not so many people know about this use of this piece of software. It's one of these like I don't know, I guess like underground tricks of the trade, but it's nice. This is one of these things that happens when you have major. So I really like efforts like Scipion and NextQIP for this reason. You have this phenomenon that happens where if everyone is using one major package developed by one group, what pieces of functionality get exposed to all of the users of that becomes the sole decision of the person who develops that software. So if it's not in CryoSpark or if it's not in RELION, most people will not use it. In the case of this is like a cool, useful thing for some specific niche cases, and most people will never discover it because most people, understandably, use these very nice integrated software packages. And so this would be a really good example of something that might be useful to you, but you might never come across unless you explore or unless you use one of these package integration solutions that is a bit more open and a bit more kind of community spirited. But I will get off my open source freedom ideals high horse now and look at the results of this M refinement. Oh no, I will look at the fact that it has refined 4 out of the 5 tilt series. Yeah, I think when people end up talking about the benefits of open source and like certain ways of building things, they get lost in this like ideological side of it. And I understand why that is, and it's very valid and everything, but it's not very understandable to people who aren't really deeply into this way of thinking and enjoy things for this reason. And so practical examples, showing people practical examples of how their life maybe got a little bit worse because of something closed or centralized is about the best that we can do, unfortunately. Open things are great. Gathering intermediate results, reconstructing and filtering. This is exciting. I'm hoping for like 4 angstroms here. If we've got a 4 angstrom map, I think we've had a pretty successful day overall. And like I said at the beginning of the workshop, the idea, I mean, I guess, Matt, how long did it take you to get your first Sub-Tomogram average? The very first time you tried?
I don't know that we have. Yeah. What resolution?
Well, I don't care about resolution at all. I just want like your sense of you were like, I'm gonna engage with this process, I'm gonna try and average something. From 0 to I had an average of something, rough weeks.
Yeah.
Weeks, okay. And that's without all of these fancy refinements and pardon?
He said hours.
Hours.
The unrecognizable flaw.
Yeah. Nice, but that's great. It means that you're the kind of like, let's get the thing done, let's and figuring out these complex systems is really hard to do. So it's yeah. The fact that we can now do this in an afternoon, yeah, I'm a little bit jaded about the tomography field. I think things could be a lot better for the most part. I don't blame anyone for the fact that they're not better. It's just like, oh, things work in certain ways and everything's a bit slow. But this is one of the few things where I'm like, a concrete signal that real progress is being made is that the time that it takes for people to learn and like be able to really do stuff is going down, at least for apoferritin. And then, you know, how you deal with the rest of your data is, yeah, potentially still a thing. Reflexively checking the WhatsApp. That's I tried to print out 3.4. Magic. Okay, so after one round of like trying to wiggle things into place and using a reference that was at like 6-ish angstroms, we've been able to improve things to 3.4. And then if we were to iterate this process and now use the 3.4 angstrom reference, we would probably be able to wiggle things even more into place. And maybe Gaia down here would take issue with the difference between 3.4 and 3.2 or whatever we had, but yeah, we are able to improve the quality of our maps based on understanding where things are in 3D, how that ends up projecting down to 2D, and then wiggle everything into place. Thank you very much, guys. This was a fun afternoon. Sorry for the we might not be able to rely on this scare. I'm very glad we were able to fix it. And yeah, if anyone has questions or anything, thank you so much. We should open the map and actually look at it because it's important to look at things and see whether or not it's really improved, right? I think I installed Chimera here. So which Chimera? Chimera? Nope. Did I install Chimera? No. Okay, well, what we will do is we will look at them in 3D mod and we will imagine 3D because we are powerful brain people. So,
Camera access. Yeah.
you guys have Chimera? How do you get to it? How do you access it?
Go to the application.
Oh, okay.
No, I use command line. I didn't do.
Here, I thought I had installed it, but I couldn't remember. I did it a long time ago, and so I don't remember.
I just searched.
Chimera X even. Wow, what a privilege. Okay, open up the Chimera. We are running Chimera X. Oh yeah, we are. Open. Okay, where is the Scratch directory? Scratch, it's there. M. Species. Apoferritin. Apoferritin denoised. Move the zoom thing. Oh my goodness. Yeah, I guess one of my things that I should be a little bit embarrassed about, I guess. Okay, soft lighting with a white background, and where is the and silhouettes. This is like my favorite default lighting camera. The zoom pass-through thing is not working. Oh God, what have I done? You all okay? Cool. So yeah, we can see alpha helices everywhere because it's apoferritin, and then as we go up and down these alpha helices, we can kind of see that look, we got these blobs sticking out. Those are side chains. Because I started out doing tomography, and because tomography has historically been like a low resolution blobby technique, not really used to looking at models and interpreting this high resolution density and things. So I'm super happy. Other people, really care about this quality of the information and how well you can place the side chains and stuff. I'm just like, oh, it's amazing. It's better than 10. So, yeah, I hope you guys are happy that you could reproduce this even if you haven't quite managed to today in the workshop. If you have managed to today in the workshop, really well done. It's not been the smoothest experience, and so we've had to work around a few things. But yeah, M does the thing.
The reason why it's called for M is just because M is like W upside down.
Yeah, it's just because M is just because it's the W upside down. Warp is, I think, because it was all GPU accelerated from the beginning, and like the little compute unit inside a GPU, an NVIDIA GPU, is called a warp.
Okay.
I think that's the reason. It's also a lot of the models that are used for everything are these grids that warp space and time. space. And so that's maybe also a little bit the thing, but you can talk about that with Dimitri over a beer at a conference sometime. I'm sure he would enjoy the conversation. He's very good at naming things. He had a thesis offer for flexibility analysis at some point that was called tilde. You know, like the little the wiggle, the little wiggly symbol. Yeah, it's really funny.